Hello, hello. Oh, I should check video quality at some point. That's good. That doesn't help. Okay. Let me see. No problem. Found some interesting things. I'm trying to just get things working. Well, we'll get there in a second, but trying to write code that does the same thing on Linux and Windows is like, sometimes it's hard and sometimes it's not, right? It's to me, it feels very unpredictable. Let's see. All cells. Oh, no, that's gonna not work again. Okay, leave. Okay. Okay, that's the noise you have to make when you're switching between operating systems. That way people know that you're panicking. Okay. I gotta see if this works. See, why is it not returning? Right? Like, it looks done. It appears done. But it's still sort of just hanging out, right? I don't think it's supposed to do that.
I think it's still doing some stuff.
Yeah. Yes, I want to shut that down. Wait, did it finish? Thought I saw something pop up. Oh, no! Oh, okay, it did. It did. It just needed to think for a minute. How are we doing? Okay, so scroll back up to the top and we see if the code's working. There we go. Okay, yeah, like the charts are being made, right? Okay. Plotting things. All the code's working so far. Wait, was that an error? Okay. I bet that's supposed to be double slash? Maybe. We'll deal with it when we see it in the slides. Okay. Git status. Oh, that's a lot. Okay. I'm going to close this. I'm going to shut down the server. I'm going to remove, or I'm going to list the .pynb files. pynb. I'm going to remove pynb. I'm going to git status, git commit, running 05 on Ubuntu. You should see the updates now. Okay. Very good. Presumably, everything's working. I have no idea. Okay. That was like such a minor error to fix, and it was very, very hard to fix. This is where we left off. Let's get back to this point, to sort of shake the cobwebs off. I opened Python 3, and I ensured that Python 3 was a Python for which I had NumPy and Matplotlib installed, right? I imported NumPy as NP. I also spelled NumPy correctly. I imported matplotlib.pyplot as PLT. I have some data called ease. There it is. Just paste that in. But realistically, you can paste in any vector for the demo. I did plot.plt plot ease. Okay. Nothing showed up, right? So then I did plot.show. And then something popped up on my screen, right? Very good. So we did that. Something interesting to note about this. This is currently on half my screen, and we note that the numbers are not stretched out. If I press full screen, the numbers are still not stretched out. What that means is that this graphic is auto-scaling to whatever screen size I put it on. So this is not an image, it is something else. Because if I took an image, and then I smooshed it in half, see, even I think the numbers are the same size regardless of how big it is, right? I think that 30 is the same size as this 30, right? So there's a little bit of stuff going on under the hood with plot.show, and we don't necessarily need to think about it too much, but I do want to point that out. This is in fact an image. We can see that it is an image, and we can see that, for example, if we zoom in, the numbers get bigger, right? It also has no titles or anything on it. Okay. So where does the image go? Well, it goes somewhere, but there's a few places it can go. This is what I see when I do plot, and we point out that this is not a chart. That is a bunch of nonsense, is what that is, right? I told you about plot.show, but I'm going to show you another way I like to save these images. When I'm making an image in Matplotlib, I'm almost always going to put it in a document that I'm going to send to another human being. Increasingly, it has been the case that I'm able to embed it in an HTML file and send it to a human being, and then it can have the sort of auto-scaling properties. But a lot of times, I think these things are getting printed out. And if they're printed out, we really want to get them into image files. The image file I'm going to recommend for you is SVG, which is a scalable vector graphic. These are infinite precision, so they look good no matter how much you zoom in. The competing form is PNV, the portable PNG, the portable network graphic, which can look fuzzy when you zoom in, but the file sizes are smaller. So I'm going to go ahead and come back over here. I'm going to plot ease. Why am I plotting again? Well, I think showing this plot consumed that plot, so I'm going to make another one. And I'm going to plt.savefig. I'm going to press right over here, save fig. And I'm going to save fig as my chart.svg. I'm going to press enter. I don't see anything. Not necessarily a bad thing to not see anything, because I also don't see anything when I say x equals 0, right? There's still changes that are made. Now what I'm going to do is I am going to Control D out of Python. I'm going to type ls space star.svg, and I'm going to list all of the scalable vector graphics in my directory. When I have two, I guess I made plot previously. Let's get rid of that real quick. I don't know what that is. So, where is it? I created mychart.svg. I'm going to introduce one additional command line technique, and I think you're on Windows, so I think you're going to type a different thing than me. I'm going to type open, and you're going to type start. So I'm going to type open, you're going to type start, and we're going to type a space, and then we're going to say mychart.svg. I'm going to press enter. And that opens. Did you get it?
Yeah.
Did you use start or open? Got it working?
I clear my all terminal, so I have to write down code again.
Okay, yeah. You can copy paste right off the next slide. This will do it all in one line.
But it's not working.
Open? Yeah, so I think you have to use start.
It opens.
Okay, start works. Cool.
Can you show me your?
That's what mine looks like. I'll make it bigger.
It's not showing me chart. It's showing me.
Let me come take a look.
Just showing this empty tab from browser.
Okay. And then how did you make the chart? Okay. Right, so you did plot.show and then you did save figure after the show. But the plot of ease has already been shown. So there's nothing in the plot when you go to save figure. If you look at my example code, yeah. And I think maybe this is the thing people don't like about matplotlib. Look at this. Plot ease, plot show, plot ease, plot save fig.
Oh, you did it again.
Mm-hmm. Sort of like putting things in the shopping cart at the grocery store and then checking out. All right, let's solve the problem you just had. It's important to do it the hard way first to build character. I was talking to some of my undergraduate students, and actually some of my other grad students recently, and I said, why do you only teach us to do things the hardest way possible? I said, it's good for you. My line of thinking has always been, and I think this happened to me a little bit in school, you have a teacher that like cares about you a lot and like wants you to learn a lot of things, so they make things as easy as possible for you, right? And then you leave school and suddenly you try and do something and you don't have someone to explain the easiest possible way to do it for you, right? So I've taken the opposite approach, which is that I say, I'm going to explain to you how to do things in the hardest way possible. And if you accidentally figure out the easiest way to do it on your own, like I'm not going to complain about that, right? That's you figuring something out. But yes, in fact, saving charts and then opening them at the command line is much harder than what other people do. Why am I teaching it to you? Because I've encountered so many students throughout the years that learned the easy way and then they don't know how computers work, right? It just doesn't seem of any benefit to the student to do things in ways that are not intended to cause you to learn. If you're working in production, you should do everything the easy way. I understand that. I'm not teaching you to work in production, I'm teaching you a class, right? Okay, so I'm going to clear my terminal. We're going to start over again. What's the first thing I'm going to do? I'm going to remove my chart, okay? We're going to go through the whole thing top to bottom. I'm going to open Python. I'm going to import numpy as np. I'm going to import matplotlib.pyplot as plt. I am going to set ease equal to... Actually, I might not even need numpy for this. Let's see, 2, 8, 8, 18, 18, 32, 32. Okay, and I'm going to plot ease, and then I'm going to plot savefig. I'm going to give it a different name this time. Even though I removed my chart, I'm going to give it a different name. So I'm going to call this chart again. This time I'm going to save it as a .png just to demonstrate I can save it as a different file type. I'm going to plot save. I'm going to exit Python. I'm going to open, and you are going to start chart again. And there's my chart. And then what's going to happen is I'm going to realize something. And the thing I'm going to realize is that my chart would earn me very low marks in my middle and high school science classes because it doesn't have labels on the axes and it doesn't have a title on the chart. And in order to change all of those things, I would have to open Python, import matplotlib, type in the electron counts, and do all of these things. So instead of doing that, I'm now going to take a different approach. Now I'm going to remove chart again, because I don't want it cluttering things up, and I'm going to nvim chartmaker.py. I'll just call it, I'm going to call it makechart.py. I want it to start with make. I am going to import matplotlib.pyplot as plt. I actually wanted that to be on second line, so I'm going to import numpy as np. Let's see. Shift-G. I'm going to press O to get a new line. Okay. Then I'm going to set ease to be equal to np.array of 2, 8, 8, 18, 18, 18, 32, 32. There might be a better way to express that series of numbers. I don't really know what it would be offhand. I'm going to plot ease, and I'm going to save the chart. We'll call it, let's see, this is called make chart dot, we'll do an SVG again. I liked SVGs. Okay, I finished with this. Escape, :x. And I'm going to run as python3 makechart.py. Notice it took a little bit of time. I'm going to run it again so you can feel it. I'm going to press enter. 1 Mississippi to Mississippi, 1.3 seconds maybe. We can time it. Okay, not 1.3 seconds, 1.07 seconds, right? I'm going to open, and you are going to start the chart. And there it is, okay? So that is a way to make a chart maker. Now, if I want to change something about the chart, it is much easier. So, this is my recommended way of doing things. On Windows, you say Start. On Mac OS, you say Open. I'm mostly doing the Mac OS things over here. And this should open your default image viewer. Okay. Were you able to get it working from a script?
Actually, time is not working.
Which one's not working?
Time.
Oh, I don't know that time will work for you. Are you in Git Bash?
No, it powers up.
Yeah, you can use it in Git Bash if you want to.
Nah, I have to do it all again.
Yeah. Well, not if you save the file, right?
Oh, really?
Yeah, because the file exists in your file system regardless of which command line you're using. Cool, got it? Cool. So, this works for you. You don't have to know time yet. Time's a separate topic. Okay. This is what you should see. Now I'm going to introduce the OS module. Why am I going to introduce the OS module? Rule of thumb is that I'm not supposed to be teaching this. I use it all the time. It's sort of like a guilty pleasure. It's considered poor practice in the sense that you shouldn't really be writing code that's just like making graphs and stuff that's also interacting with the operating system. That seems like a bit much. But sort of my pitch for this is, well, who else is supposed to look at a scalable vector graphic or a PNG file? Kind of the only two entities I think should be looking at those things are dedicated software that's run by my operating system or my web browser. And it seems like the web browser is just as much of a mess as the operating system, right? I'm supposed to teach you about subprocess, which I find to be an absolute nightmare to work with, right? So, what are we going to do? I'm going to open Python. Well, no, I'm going to clear my command shell. I'm going to open Python, and I'm going to import OS. It stands for operating system. Okay? That's all I'm going to do. We can take a look at OS. It's a module, OS. It's frozen. OS will behave a little bit differently on Windows, Mac, and Linux, but the thing we're doing is not going to be that different. So let's go ahead and do that. I can issue commands as if they're shell commands with os.system. Let's take a look at an example before we do open my chart. Oops. Ooh, I don't know what button I just pressed, but I didn't mean to press that one. Where do you think we are? Probably around here. There it is. Okay. So, I am going to say OS. I'm going to say os.system. I'm going to type ls, and it's going to list the current files. I can os.system remove chart.svg, and then I can os.system ls and see that chart.svg is gone. I can run the code in make chart by typing import make chart, and then I can see that the chart was made. I can remove the chart again, and I can generate the chart again by saying os.system Python 3 make chart.py. What this is I have a command line bash shell running Python that opens a command line bash shell that runs Python. And it works just fine. And I can see that my chart is generated. I can os.system nvim chart make chart.py. There we go. Okay, so I've typed os.system, and I'm going to use os.system to open nvim. Okay, there it is. Then I can exit nvim, and I exit nvim back into Python. And then lastly, I will os.system, and I will write open, and you will write start chart, or whatever you're going to name your chart. And there's my chart. And I opened it without leaving Python. How you doing?
Yeah, I need to.
You got it? Now, we should convince ourselves this is actually working by importing matplotlib pyplot as plt. And we should plot something else. What's another series of numbers we should plot? Let's plot the Fibonacci numbers. 1, 1, 2, 3, 5, 8, 13, 21. Okay. plt.plot fib, plt.savefig chart.svg, and then I am going to open the chart. And I have a new chart. Or I guess I added it to my old chart. Cool. So I'm able to alter this chart. And still plt.show. And I think if I plt.show twice, then the second time I get a new chart. Yeah, there's not a current chart there. Okay. There we go. We can get just the Fibonacci's by showing, replotting the fibs, resaving the file, and opening the file. Okay? There it is. Ta-da, the Fibonacci numbers. Congratulations to them. Look at that. Very nice. I don't know. Probably approximately exponential curve. So, that is the OS module. Use it responsibly, or don't use it, but it seemed too cool to not show you. Let me show you another way we can use it. nvim make chart.py. At the beginning of this line, I'm going to press O instead of I. What is that going to do? It's going to make a new line and put me in insert mode. So I'm pressing O, new line in insert mode. I'm going to import OS, and I'm going to os.system chart.svg. And then I'm going to realize I shouldn't be typing chart.svg twice, so I'm actually going to make a variable that represents the name. I'm going to call it file name equals chart.svg. And then I'm going to use the variable name in two places. I'm going to save and exit with %x. Do you want to see anything before I close this?
Yeah, it is.
Okay, I'm saving and exiting. I'm going to Python 3 make chart, and I'm going to think about what I expect to happen when I run this file. Here, we'll take a look at it first. So what I think is going to happen is I'm going to make a plot. I'm going to save a plot to the file system. From the file system, I'm going to open and view the plot. That's what I expect to happen. Ooh, chart.svg not found. It didn't work. Why did it not work? Oops. I'm going to try and run it in the shell to see what happens. Ease is not defined. Okay. Oh, it's not os.systemfname. Hold on, okay. No, that's not what I meant to do. Okay. nvim, make chart. It is open, and you will write start.
But it worked for me.
It worked for you?
Without open or just F9.
Oh, it just worked with fname?
Yeah.
That's cool.
See?
Well done. Okay, so you were able to just type chart.svg and it just opened. That kind of makes sense.
Python 3, then.
Yeah. As long as it works and you have a system that works for you. And there, I got it to work for me as well. Very cool. So that's what ultimately worked for me, but doesn't matter. I am going to do one arrangement. I'd rather do all of my imports in the same line. So I'm going to put OS up here. Cat make chart. And so I think that's something I'm pretty happy with, right? I import 3 things, I define 2 variables, I plot and save, and then I open, right? I think it's, for me, it's quite convenient that the time where we have to input different commands to different operating systems, open and start, we also do so with the operating system module, right? So everything's named operating system. It's operating systems all the way down. We're only talking about operating systems. Operating system this, operating system that, right? Okay. Very good. You are, as someone that is learning this material now, you should learn about the subprocess module. You don't get to learn about the OS module like me. The OS module is a dinosaur. It's a relic of a bygone era. It's not something you're supposed to use anymore. So you're supposed to do as I say, not as I do, and you're supposed to use the subprocess module. How does the subprocess module work? I have no idea. It seemed complicated. I've copy-pasted other people's code and it worked just fine. So use subprocess instead of OS when you're checking Stack Overflow and trying to do things, right? But why did I show you OS? I suspect if you're ever looking at scientific code, I think if you're looking at something written by someone at Lawrence Livermore Berkeley, it's Lawrence Berkeley National Laboratories, LBNL. I'm guessing they're using OS in that code because I'm guessing they wrote the code 15 years ago. It runs fine on their systems. There wasn't a reason to switch to subprocess, right? They're probably cloistered internal systems on an intranet. They're not coming under security attacks. They can take these shortcuts, right? If you are deploying web servers onto AWS, do not use OS. Use subprocess, right? So that's kind of the difference. So I'm going to teach the older, easier, less snazzy version, which is OS. Okay. I did this demo already, but you can open Python, open nvim inside of Python, write a script inside of nvim, close nvim and still be in Python, import the script you just wrote inside of Python. So what this means is now if you've been in the Python command line for a while and you have a bunch of data saved and you don't want to regenerate all of your progress, right, but you need to develop a function, you can actually do that. You can open nvim, write the function in nvim, exit nvim, load into Python. Now, of course, you could already do that in another way, which is I can have Python over here. Hi, it's me. I can come over here, nvim some script .py, print hello, it's you, save and exit, import some script, hello, it's you. Ta-da, like you could already do that, right? But now you can do it all within one terminal window. And this is mostly useful when you're attached to someone else's remote server doing a scientific computing workload, or when you're attached to AWS or something like that. Okay, let's talk about plot elements. The other day I made a chart and I posted it to our little faculty group chat, and I don't label my axes or titles, and they raked me over the coals. I was getting bullied. They were saying, Calvin, you don't know what you're doing. We're never going to let you teach data visualization ever again. You have to make all those students add titles and X labels to their charts. So I'm going to do that to you, right? This is a do what I say. Now, I was perfectly happy with that chart I just made. I happened to know what all of the axes represented, right? It was clear to me, right? But let's do some examples. And so to do some examples, let's recall the taxes array. So let's go ahead and grab that. Let's continue to practice getting in and out of Python. So I'm going to import numpy as np. I'm going to import matplotlib.pyplot as plt, and I'm going to drop taxes right here. Boom. Taxes placed. Okay. Let's go ahead and plot taxes, and we're going to see this graphic, and it's going to look horrible, right? So we'll do plt.plot taxes. I'm going to do plt.savefig. Chart.svg. I'm going to import OS, and then I'm going to os.system. I'm going to write open, and you're going to write start. Chart.svg. There it is. Same graphic, right? These were in fact now actually generated on the same computer because I just regenerated all the graphics. That doesn't really tell me anything about taxes, right? It doesn't actually tell me anything about anything. This doesn't tell me anything about nothing, they would say, right? We appear to have an orange line here that is just 0, you know? Not terribly exciting. So what are we going to do? We're gonna exit out of that window, and let's actually look at some proper graphs. Okay, so what I'm going to do now is I'm going to split up that data. I'm going to look at taxes, and I'm going to notice that what I'm looking at looks an awful lot like an x value and a y value. I think the x values are the amount of money made, and the y values are the marginal tax rate, and I want to plot x by y, so I'm going to do that. I'm going to make something called x, which is going to be taxes, and I'm going to look at only the ground floor of all of the apartments on the road, right? So x is all of the tax bracket cutoffs. Then I'm going to look at y, which is going to be taxes, and I'm going to look at all of the first floors on all of the apartments on the block, right? And those are going to be the marginal tax rates, right? We're not going to go up to 39.6%, okay? Then I'm going to say plt.plot, and this time I'm not only going to provide a single array. I'm going to provide x values, I'm going to provide x values, and I'm going to provide y values. I'm going to plot.savefig as chart.svg, and then I am going to os.system. I'm going to write open, and you're going to write start, chart.svg. Or you might not have to write either, as you said. Oh, that doesn't appear to be what I tried to do. That appears to be extremely silly. Do you see how silly this looks? Look at how silly it is. That's outright terrible, right? going to do plot.show, clear everything out. Then I'm going to plot.plot, I'm going to plot.save, and I'm going to open chart.svg. And there's the chart I was looking for. Okay. Oh, that's very little. Okay. Do you see something that looks kind of like this? Here's mine.
Can you?
Here's another way we should do things. I'm going to exit Python. I'm going to nvim chart maker. Ooh, that's not what I meant to do. Okay, exit. Nvim chart. Make chart. Okay. Let's go ahead and put taxes in this file. Now I'm going to plot. What am I going to plot? I'm going to plot taxes, ground floor, taxes, first floor, fname. Okay, I'm going to go ahead and save that. I'm going to Python make chart, and I'm going to see this graphic, and then I'm going to cat make chart so you can see what made it. Do you have all that working? You got it? Cool. That's a different shape.
And just one space. You have space after open, right?
I do, yes.
I did not have the space after
Okay.
so that's why it was giving me an error.
Yeah.
And you know,
I want to try something. I'm going to reverse the 1 and the 0. Is this the shape you have?
yes.
Okay. So the difference is this line.
But I have this other line showing on the board.
Okay. Oh, okay. Are you doing perhaps this?
But I did that the first time.
Do you have this?
Yeah.
Okay. And so why is that? Because you're just plotting taxes directly. Right?
Yes.
Okay. And what are we trying to do? We're trying to plot income versus marginal tax rate. That's not what this shows. So we're going to modify. Here, we're going to open NVIM make chart. And I wonder if we can just transpose this thing. I'm going to try transposing it and see what happens. Taxes dot, it's probably taxes equals taxes dot transpose. Ooh, that's pretty. It's not what I was looking for, but look how pretty it is. Okay. So we're going to NVIM make chart. We want incomes equals taxes, bracket, colon, comma, 0. We want the ground floor of every apartment, right? If we're not sure, we can even just print those out. We can say, hey, these are incomes. And then we want rates, which equals the taxes. Every single tax on the block, but we want the first floor of the house. And then we're going to plot incomes versus rates. Can I see it? Good job. It looked a little suspicious last time, so I wanted to see it again. Okay. So, we've done it. We've done whatever it was we were doing. And now let's start fiddling around with it. So we're going to create an array of possible incomes. We're going to calculate tax at the income, and we're going to plot that tax. So how are we going to do that? Well, fortunately, we already have single tax, which is the tax rate at every point, right? So I'm going to go ahead and grab this, and I'm going to put it in my chart. NVim make chart. I don't think I need any of these things anymore. I'm going to paste that in. Okay, there's taxes. Got single tax. Okay, cool. All right. So this is going to be the tax rate at any income value. I think this is correct because this is taken from the solutions to a previous problem. So we're not necessarily debugging this right now. This is just to the use NumPy thing. Okay. So let's consider some possible incomes. I'm going to introduce something here new. It's called np-arrange. And what am I going to use np-arrange for? First of all, let's get rid of the rest of this file. I'm going to press escape to get into normal mode. I'm going to press D to get into delete mode, and I'm going to do Shift G to delete the rest of the file. Okay? Then I'm going to press O to go back into insert mode and get a new line. Okay, so I got some new lines. So I have single tax. Single tax is of some income. I want it to be of all incomes, right? So let's go ahead and figure that out, right? Incomes equals NP, and what is an arrange? Well, an arrange is a series of values across, I don't know, some range. So we can take a look at it. Here is one example, np.arrange 10. It's the numbers that range from 0 to 10. Here it is to 400,000. That ellipsis in the middle has approximately 400,000 numbers in it because this is only 6 of them, which is a very small subset. Maybe we don't need every number in the range. Maybe we can start at 10,000. 10,000. And maybe we can take steps of size 10,000. That doesn't look too bad, right? Maybe we can take steps of size 100,000. And then there's only a couple of those, right? So this is basically the same thing as slices. We're just taking slices of numbers, right? So there is an example of an incomes range. We can also use a linspace. I see linspace all the time. The difference between a linspace and an arrange is integer numbers in some range, and you don't say how many numbers you want. Why is that a problem? Well, we have incomes that are going to go up to around 500,000, which means Matplotlib would have to plot 500,000 points. That's a very large number of points, and I know that because my screen is 2,000 pixels across. So it's not going to fit 500,000 pieces of information on that screen. So my computer will be working very hard for no reason. So we can instead use a linspace, a linear space, and we can say, hey, we want to go from 10,000, is that 10,000, to 400,000, and I want 5 values. Make sure they're evenly spaced. And it does. Those are 5 evenly spaced values, and if you get 10 evenly spaced values, there's your 10, right? You can also start at 0, which is much more common. So there's 10 evenly spaced values, but this is going to look really nice if we do 40, right? Oop, probably want 41. There we go. All right, so that's kind of how linspaces work. My recommendation is we just take a linspace, maybe up to $500,000, and we take a look at it, right? So I'm going to go ahead and do that. Incomes equals np.linspace. I'm going to go from 0. I'm going to go to 500,000, I think. Yeah. And I'm not going to specify how many values I want. I think if I don't specify how many values I want, it just guesses. And that seems fine. np.linspace 0. Looks like it gives you 50 things. That seems fine. It seems like 50 points on my plot is going to look pretty good, right? So we'll just go from 0 to 500. Actually, I wonder what happens if I just if I take out that 0. Nah, okay. It's required to have 2 things. Okay. So that's a linspace. Linspaces I mostly experience in terms of plotting, right? We'll use them a little bit to interpolate missing data as well. So when we know there's something going on in between 2 numbers and we want to take a look at all of them real quick, that's sort of when we use linspace, right? So I do want to point out, and this is an aside, this is not something I use often, but when I learned NumPy, this was one of the things people always taught. You can make an array of all 1s, and you can make an array of all 0s. And you can make these things in, I think, however many dimensions you want, right? So if you want 2 by 2 by 2, maybe go for it. Maybe that's not allowed. Okay, maybe it's not. Oh, maybe you do this. So you can sort of have arrays of all kinds of size that you make out of 0s and 1s, right? You can make the same thing out of 1s. You might see this around. It doesn't seem to me like people use 1s and 0s like this that much anymore. Also, these are noteworthy. That is decimal 0. So if you want integers, you have to put a little bit more work in. So I just thought I would bring that up while we're here looking at a range, and linspace are the things that I think people use instead of 1s and 0s, but I think there's a lot of code around that still use 1s and 0s. These are, by default, floating point values. We can take np.1s. We can take 3 of them. We can divide it by np arrange. I'm going to do 2, so I'm going to divide it by 2, 3, and 4. 2 to 5, and step size of 1. Okay. I don't think I need the step size, do I? Okay. So I get 0.5, 0.33, and 0.25. Now, it might be the case that I want to work with integers, and I do that by specifying an integer type. I say dtype, which is the data type. I set it equal to int, or perhaps equal to np int 64, I think is something we've seen. And then I'm going to double divide, and I will get all 0s back. Because 3 divided by all of those things is 0. Oops. There we go. So 3 divided by, or 1 divided by 1 is 1, and 1 divided by everything else is smaller than that. Does that make sense to you? Do you know what you're looking at here? You made a face here. So that's all 1s. What's 1 divided by 0? It's an error. Yep. What's 1 divided by 1? It's a 1. What's 1 divided by 2? Well, it rounds down to 0. Oops. Rounds down to 0. Rounds down to 0. Rounds down to 0. Okay. So that's what's going on here. All right. Let's go ahead. Let's go ahead and have some taxation. How are we going to do that? We have incomes. No, I still don't want full screen here. I want to show the code next to it. Okay. So here is, I did 100 points in this one. We're just going to do 50 points here. I think it's going to look the same. Now, here's the thing. Actually, we'll just go. I'm going to take this code literally exactly. I'm going to copy it. I'm going to throw it in Python. Okay. Boom. I can compute single tax of 100,000. No problem. I can look at incomes. I didn't define incomes. That's okay. Incomes equals np.linspace. 0, 500,000. Okay. I can look at incomes. There it is. So it's a bunch of values. Okay. I wonder if I get really even values if I do this. Yeah, interesting. So, okay, right, we've got, oh, I see the reason I did 100 last time. You see what's going, there's nothing in the lowest income bracket. If I divide the range into 50 parts, 0 of the parts fall in the lowest income bracket. See, because that's already in the second lowest. So I should, in fact, say $100. And then I see one income that is in the low tax bracket, right? Really shows how small it is before they start turning up the income tax, right? Someone making this much money is below poverty line and still taxed at above the minimum rate. Okay, so I got that. And I got single tax. And a lot of times, if I take incomes and say multiply it by 0.396, this is one example of tax, right? And that's funny, got everything to line up exactly, because the difference in scaling. I bet that's why it's 0.396. When they were setting the tax policy, they did this. Okay, that's hilarious. Okay, so I would perhaps expect that I could go single tax of incomes. That's not allowed. The reason that's not allowed is because if we look back at single tax, there's a loop in here. We can't loop over every element of a vector. That doesn't make any sense at all. There's kind of two ways to deal with this. One of them is by using a NumPy piecewise function, so I introduced piecewise functions, and the other is by using vectorize. I'm going to use np.vectorize, and what does np.vectorize do? It is a function that takes a function and produces a new function. The new function works on vectors and the old function doesn't. That's all it does. So let's take a look at that example. So this does not work. Single tax incomes does not work. We're going to say vector tax equals np.vectorize. Do you think I spelled it right? I think I did.
Yes.
This is why I write scripts instead of in the REPL. Okay. By golly, that looks like it works. I'm going to vector tax incomes, and I think it's going to work. Hey! And these are about how much less you'd get. Remember, I think we found that people in the top tax bracket get $53,000 off their taxes or something, right? And that's about how far apart these are. I guess that's $43,000 off. And yes, these people are paying 10% instead of 39.6%, so that should be 4 times bigger. Okay. We can also say costs equals vector tax incomes. And this is a time I sometimes use slices just to look at fewer values, right? That can be nice. So those are all the things that I got up to in order to try and plot income tax. So let's go ahead and put everything together. Here's single tax. Here's incomes. I'm going to vector tax. I decided to put a 100 here. Vector tax equals np.vectorize single tax. Okay. And then what am I going to plot? I'm going to plot plt.plot, and I'm going to plot incomes versus the vector tax of the incomes. I'm going to close all of my parentheses. I'm going to plt.savefig as my chart, or just chart.svg, and I am going to os.system. I'm going to write open and you're going to write start, and then we're both going to write a space. Then we're going to close the quotes only after we write the space, and we're going to add that to file name. I'm going to save this. I'm going to cat the file so you can see it if you want to look over. And then I'm going to Python 3 make chart. We're doing okay? I think so.
Is this code?
Okay.
It's giving error for the FNAM.
Okay. Name is chart.svg. So open nvim. Go to the last line and click on the comma. What is that comma doing?
Comma.
You can either use plus or comma, but you can't use both.
Thank you.
Yeah, no problem. I believe, we'll see if I'm correct. I think you can either put, and this is dumb, I use Shift G to go to the last line. I use /+ to search for the plus sign. I hit enter because I found the plus sign I want. I'm going to press R to go into replacement mode. I'm going to press comma. Press escape, :X, and I believe this still works. Nope. It works if you print it. Shift G, /, comma, replace, plus, nope, enter, replace, plus, escape, :exit. And no one will ever convince me that that combination of keystrokes is slower than moving your mouse. I just don't believe it. It's like 6 keystrokes. I can type at like 120 words per minute or something, right? I just have to be able to remember what the keystrokes are. Did I play monkey type with you last time I was here? You remember that? Okay. Well, we have to do a monkey type break. One of the things I like to impress upon everyone is the fact that you can probably type much faster than you think you can. You can certainly type faster than you think, right? And so one of the ways to demonstrate this is to go to monkeytype.com and type as fast as you can. You will be shocked by how fast you can actually type, right? Now, I understand there's a variety of ways on here where you can get this to like let you type C++ and things like that. I don't really know how to do that. You can probably type in a non-English language if that's more comfortable for you. Contractions, misspell, double letter, Shakespearean, old, medical. You can do Thai, Croatian. I know a bit of Croatian, not as much as I'd like. Esperanto. We can do some Python code. I saw it somewhere. Where is it? Python. There we go. So here's some Python code. And let's see how fast I can type this. I don't like those double underscores. So that's pretty fast, right? And I think that's probably about as hectic as typing Vim, right? And then now think, I'm going to try and move the mouse and click somewhere on this keyboard. The thing I'm going to do is I'm going to try and restart it. And how much slower is that? Okay, so first of all, I have to put my hand on the touchpad. Then I have to figure out where my cursor is. Okay, I see the cursor. Now I have to figure out where to click. Okay, I guess this is next test. To go back to English, I have to do all of this stuff. It's just slower, right? And it doesn't feel slower because we're used to doing it, and we're used to there not being an alternative. There's no way to navigate this website with keystrokes, right? I wonder if there's Vim in here. Code Vim, there it is. Okay, this is going to be slow for me, but you can practice this, right? The thing I'm noticing is I don't have typos on this because it's slowing me down enough. Oh, this is a search. Right, so 44 words per minute? I can't say words that fast. I had 94% accuracy. Look at this, and look how fast I was in the short section where I actually knew what I was typing, right? So you can type much, much faster than you can move your hands. You can type much, much faster than you can think, right? So if I want to change something in make chart, for example, if I just want to reverse the x and y dimensions, right, I can just nvim, plot, enter, go to the end of the line. Nope, that's not the plot I wanted. Okay, n, enter, n, end of the line. I can de vectors. I can go to the end of the line. I can insert comma, paste, and go back, x, save and exit. And I can just change my chart directions just like that, right? It's so fast. And all you have to do is be clear on your thinking. Another thing that I think happens, and I mostly see this with students in like writing classes, is they feel like the process of slowing writing down is that they can't type quickly, and actually the thing that's slowing the writing down is they have no idea what they're doing, right? So oftentimes I think when you're writing code, you'll be like, or like you're in NVim, right? And you're like, like this editor is slowing me down so much, but you don't know what you would type if you could type, right? And you're blaming the editor, right? Because if you really know what you could type, right, you would be able to realize what the NVim commands are to input that text, right? If you really knew what was wrong with your code, you could find it quickly in NVim and fix it, right? The thing that's slowing you down is actually not understanding the code. It's not understanding NVim. And I think once we stop sort of hiding behind those excuses, right, like finding that comma is like an interesting thing to do, but you have to be able to do that. You have to be able to find loose commas in your code, right? And helpfully Python at least told you what line you were looking in, right? I even wonder if you just deleted that line and retyped it, if the error would have gone away, right? And you would never know why it fixed it, but you would have learned an algorithm. Okay, let's plot some vector functions. Let's take a look. Okay, let's also plot tax rate. Tax rate to me is way more interesting, so let's go ahead and plot tax rate. I'm going to open my chart again. Nope, that ran it. I'm going to nvim my make chart again. Nvim make chart. We're going to go to tax incomes. Okay. Oops, wrong direction. Okay. So I am here in vector tax. Let's see. I'm going to get rid of the rest of this line. Okay. So what do I want to do? I want to plot incomes versus how much I spend on tax. The amount I spend on tax is vector tax of incomes, but I'll just say costs equals vector tax of incomes. And then we will say cost divided by incomes. And this will plot the percent rate. This is solving a problem, the challenge problem from the first day, which is where is 35%, right? I can now just see where two lines intersect. I don't remember exactly what the solution was, but I'm going to go up to 600,000 here. And I'm actually going to plot two things now. I'm going to plot the vector tax of incomes, and I'm also just going to plot what am I going to plot? Incomes 0.396. Can I do that? I don't know if I can do that. Maybe. I'm gonna try it. Okay. Python, or nope, I'm gonna show the text so you can copy. Okay. Python, make chart. I did mean costs. Okay. Right, okay, so here's an error in line 25. Cost is not defined. Do you mean costs? Yes, I do. Search for cost. Space. There's only one instance of cost space, right? And so when it said, did you mean cost, all I had to do was search for cost. I press enter, and then I go to the end of the word with E, and then I insert an S. Okay. Yeah, it needs a vector. Okay. just going to have 100 0.396s. Or no, it was, we were finding 0.35. Okay. So we can see where these two things might finally converge, right? We got to extend our range. Let's go out to 100,000. I, 1, 0, delete, escape, colon, X, up arrow twice, run make chart. And there we see it. Right there. We finally intersect the marginal tax rate that kicks in at $190,000. So the marginal tax rate is that high over here. And it takes that long to get up to, we could say paying your fair share, we could say getting gouged, depending on how much you get paid, right? But there you go. There is a graph solution to a numerical problem we had earlier. Very cool. I had an error on this slide and I just refreshed and it went away because I rebuilt in the back end and pushed them, right? So, invalid value countered in divide. Okay. I don't think that affects me. Cool. On to the next thing. We can plot these things against each other. Here's income cross costs versus income cross costs divided by incomes. Realistically, those should be on different scales. What different scales should they be on? I don't know. That's getting to be outside of my field. The only thing I'm telling you is that you can plot two things on the same axis, right? And let's get into chart elements. Do you have any questions of any of that stuff before we go on?
No.
You got it? Cool. You feel pretty good with the Open, NVim, Python? Yeah, we'll just keep practicing. I mean, a lot of these slides are just to get your hands doing the motions so that if you don't think about it for a week, you have a chance of doing it again. Okay, so yeah, I think what I've been taught is that charts should have labels on the vertical and horizontal axes. They should have a title and they should have a legend. So we're going to add each of those things. First thing we're going to add is a title. That's going to be easy. I'm going to open NVim make chart. I'm going to go to the end. I'm going to go up 2 lines with K. I'm going to press O to get a new line and enter insert mode. I'm going to type plt.title. What am I going to title this thing? Income tax rate by income. I'm going to say it's in dollars. Okay. Cool. That seems fine to me. I'm going to press escape colon X. I'm going to type up twice and then I'm going to press enter and I'm going to see what my chart looks like. Okay. Oh, by golly, it has a title on it. Look at that, it has a title. Now I know what I'm plotting. Now if I show this to someone else, they won't say, "Why do you just have a squiggly line on your screen?" Right? I spend a lot of time sitting in coffee shops typing away, and I don't want people to think I'm just making squiggly lines, right? I want them to think that I'm thinking great thoughts, right? And I am thinking great thoughts. So my plots should look like I'm thinking great thoughts. The dean of the other school I teach at is named Jameson Watts, and so I made a Christmas carol about him. And it goes, Jameson, Jameson, Jameson Watts, Jameson's plots and Jameson's thoughts. And everyone hated that. So anyways, you can sing that to yourself if you want. And anyone's name fits. Yeah, could you do your name? Camera. I don't know. There's a way to line it up.
Yeah, there's.
Yeah.
I never tried it. So.
Yeah. Cool. Let's label some X and Y axes. What do you say? Good idea. That's what I say. I'm going to look for title. I'm going to press enter to get out of search mode. I'm going to press O to get into insert mode on a new line. I'm going to type plt.xlabel. What is the X value? Well, I know what the X value is because it's incomes, right? It's incomes in both of these plots, right? So we're going to say income in dollars. Very cool. And then we're going to plt.y label. What's the Y label? Well, the Y label is two things, but both of them are fractions, right? One is cost divided by incomes, which is tax rate, and one of them is the 35% line. So that is the tax rate And I think that's all I got to do, right? So I'm going to go ahead and press escape :X. I'm going to type up twice, and then I'm going to Python make chart. And, oh, would you look at that? Income in dollars is labeled, and the tax rate is labeled. There's a little bit of a goofy thing going on here, which is that these incomes have been converted to scientific notation. So what I actually need to do is say this is incomes in millions of dollars. So I'm going to update my chart. And Vim. Okay. And I'm going to search for in dollars. Dollars is a special value in the search term, so I'm actually going to search for in. I'm going to press enter to go to the first in, and then I'm going to press N to go to the next in. I'm going to press I to change into insert mode. And I'm going to say income in millions of dollars. Did you need to see that? Got it. So you put 1 millionaire on the chart and all the dollars are in millions of dollars, right? That could be operating system specific. I don't know if that'll happen to you. Okay, I solved an error. I'm going to tell you what it is. I was getting an error for divide by 0. That's because my first income was $0. I just changed the lens space to begin at 1.
Yeah.
I got my error to go away. So that's much nicer, actually.
What did you do for the...
So I changed my lens space to begin at 1 instead of 0. And the reason is because I'm dividing by it. I should not divide by 0. I can put it as small of a value there as I want, right?
Okay.
That's the only thing I changed.
Yeah.
Right there. That should be changed over here, probably. Do I have it open anywhere? Wait, that's odd. I definitely built in both of these places. There we go. Lens space. Oh, maybe they're all fine. Okay. So that should be 1. Okay. Build that in the background. Cool. So we have this graphic here. We'll go ahead and keep at it. Okay. Income, whatever. This is the graphic I made. We can add a legend. But can we really add a legend? I don't think we can. So let's go ahead and pop in NVIM. I'm going to go to the end, and then I'm going to go up 3 or something. Yeah, we'll put it ahead of the labels.
What's the legend? What is the legend?
A legend, so if my graph has multiple lines on it, perhaps with different colors, a legend labels what the colors represent.
Oh, okay.
And it'll be much easier to understand what a legend is once we make one, right? So I'm going to say plt.legend. That's all I'm going to do for now. I'm going to make the chart. And I got a note that says, no artists with labels found to put in legend. Note that artists whose labels start with an underscore are ignored when legend is called with no argument. So what does that mean? Well, the thing we should take away is there's no labels, okay? This is the legend right here, there's nothing in it. You probably wouldn't even see it. So what we need to do is we need to add some labels. And we're going to do that with label. We're going to add label to our plots, okay? So let's go to plot. We want to go to dot plot. Well, here, we'll go to plot comma, or paren, okay? We're going to go to the end of this line. We're going to insert, we're going to say comma, label equals tax rate. We're going to go down to the next line, and then we're going to say second highest marginal rate. I'm going to save that. I'm going to cat it so you can see it if you're following along. I'm going to Python 3 make chart, and a chart's going to pop up. I'm going to put it on this screen. This is what a legend is. So I have a blue line. Is that?
Oh, okay.
You've seen these before. Maybe you didn't call them that. Okay. Cool. Then we added a legend. We can also add a note. Notes are not exactly the easiest thing to add, but I really like them. The most persuasive data visualizations I've ever seen are usually about minimum wage or cost of living or something which changes in the United States, and all of these charts have a massive inflection point in 1980 when Ronald Reagan was elected. And so the charts don't make any sense because they look like a measurement error, and then you see, oh, there was a major U.S. presidential election at this point in time, and you're like, oh, U.S. federal policy changed. That's why all of the numbers changed at that time, right? Because you're thinking, you're like, geez, what was going on in the 1980s? Was it like, was there a war? Was there global warming? It's like, nah, it was just a change of government, right? And many Americans don't perceive Reagan as a change of government, right? But it kind of was. So we're going to add some annotations, and I'm going to do an example of an annotation here. So we're going to go into NVIM make chart. I'm going to go pretty much to the end of the file. I'm going to do everything except save. All good. I'm gonna label this because this is going to be involved. Add an annotation. So I'm going to annotate median income. Median income is, it's not exactly $40,000, but it's probably about $40,000. The median tax, therefore, is whatever the single tax is on $40,000. It occurs to me this is inaccurate because I looked at median household income, and this chart is actually only showing the rate at which you would be taxed if you're single, but probably not every household is a single wage earner. So we're doing our best here. The median percentage, therefore, is the median tax divided by the median income. Okay. And that means that the XY values are median income, comma, median percent. This is multiplied by 100 here. I don't actually know if that's correct. So I'm going to try it without multiplying by 100 because I just plotted 35 here, 0.35 here. So I don't know why there's a 100 there.
There is error. Mat PCT equals to is missing.
What's missing?
Yeah, in your NWIP.
Over here?
Mat PCT
Yeah.
equals to is missing.
Okay.
Yeah.
There we go. That took me forever to see. Okay. Thank you. Yeah, there's a lot of med PCT.
Oh, I should have.
Yeah. Out where I'm from in Portland, PCT means Pacific Crest Trail. It's the trail. Pacific Crest Trail. It's like
Crest
a
Trail.
2,000-mile hike. I bet if I type in PCT, that's what I get. Pacific Crest Trail. Yeah. So I was like, why are you talking about the Pacific Crest Trail? It's like, oh, I used it for percent. Okay. We're going to use plot.annotate. Okay. So, plt.annotate. We're going to annotate the term median income. And we're going to annotate it at location XY. I see. I was multiplying incomes times 100, so that's why I had to multiply this percentage times 100. But I'm currently not multiplying these by 100, so I don't have to do that. So what am I providing? I'm providing a label, and I'm providing an XY value. Okay, there we go. So I'm going to press escape. I'm going to press colon. I'm going to press X. I'm going to press enter. I am going to cat make chart, so you can see it. And then I'm going to Python 3 make chart. And there is my well-labeled graphic. Got it? Cool. You're a proper scientific computer. All right. Here's something that I thought was really nice. I liked this a lot better writing a function. So this is the function that takes an income and a note. Let's add that. I'm going to open NVim. I'm going to define another function. Call it add note. We take an income and a note. Okay. And I'm basically going to grab the annotation stuff. So I'm going to scroll down here. Now, the way I usually do copy paste is as follows. I get into normal mode. I press V, which is, I'm pressing V. V as in Volkswagen. V on my keyboard. And then I'm going to use movement keys to select a number of lines of code. This is called visual mode, so it's going to highlight text. Okay? I'm going to press J a couple of times, which is going to move the cursor down. Okay. So I highlighted all of that text, and I moved the cursor down.
What is key for the undo of the side?
Just you.
You?
Mm-hmm.
Yeah.
Okay. So I highlighted this, and now I'm going to press D. And all of this text is going to go away, but it's going to be saved as the most recent thing I deleted. So I'm going to press D, and then I'm going to go up a bunch. So I'm going to press K a few times, and then I'm going to paste that back. See, it still says 8 fewer lines. I've got my 8 lines at the bottom of my screen here. So I'm going to press P, and that moves the text. I'm going to get rid of that extra line. I grabbed an extra line by accident. I also want to indent all of this, so I'm going to go into visual block mode. I'm going to use Control Q. I'm going to press J. It's probably 5J. Yeah. So I went down 5 lines. I'm going to enter block insert mode with Shift I. Then I'm going to press Tab. After I complete my insert, I'm going to press Escape, and it's going to apply the insert to all of the lines. Now we're going to do a few more edits. All these meds should not say med, so I'm going to get rid of the med. How do I actually want to do that? I'm going to try and do that with a find and replace. So I'm going to do %s, which is going to search for a string. I'm going to search for med underscore. And I'm going to do another slash, which is going to replace that. I'm going to replace it with nothing. Oh, that's only getting the first one in a line. It's interesting. I didn't know it did that. That's fine. And I'm going to go ahead and press enter. I'm going to delete the other meds with D3L. Nope, it's D4L. 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 Okay. Rather than income, I'm going to have a note. So I'm going to delete income, and I'm going to say instead note. And instead of income being defined, we're going to just put it in here. Okay. I'm going to clean up some loose lines, and then we're going to add some notes. Okay. So the first note we're going to add is we're going to add median income at 400,000, and then we're going to add BSCS income at 800,000 or 80,000. I don't know why I'm saying 100. I'm going to save. I'm going to make chart. Oh, did I goof? I goofed. Python and Vim. I have an error in line 23. Oh, I did my note and my income backwards. I'm just going to change the order. Inc is not defined. Oops. Undo. We'll just use inc instead of income in all these places. Okay. There we go. And I was able to label the median income and the computer scientist income. I said BS because that's for labor market for new graduates, so that's people graduating this year. Some of them might have a BA in computer science instead of a BS. I don't know. But that's the undergraduate degree this year that we labeled. Well, I think that's a pretty interesting chart. Do you feel like a sociologist yet?
Yeah.
Okay, cool. Good job. I put a bunch of other things on this chart. I did median income, new grads, physics new grads do well, and CS mid-career I also labeled on here. So here's a variety of things you can look at, right? And that's another way to do it. This one doesn't have a legend on it because it doesn't need it. I have already shown an example of plotting different things on the same plot, but we can do that here as well. So this is the multiple functions section. I think, did I close it? There it is. Right, so mine already has this 35% on it, but that's not really a function, right? I've sort of only plotted one thing. So let's go ahead and do another plot. And we're going to show what the marginal tax rate is at each point versus the actual paid tax rate, right? So the reason this was interesting to me is when I was growing up, I was frequently around adults that talked about like how high their tax rate was. They're like, I pay like 30% in taxes. But none of those people were making $1 million a year, which is when you start paying 30% in taxes, right? So they were talking about the marginal tax rate on their last dollar, like it was the rate they paid, right? But really, most of the taxes they were paying were at like 15% or 25%, right? And that's just psychologically interesting, you know. So let's go ahead and write up a bracket percent real quick. And I think we're clever enough to figure this out. So I'm going to nvim makechart.py. I'm going to look for the first return, because I want to go right here, right? So I'm going to search for return. I'm going to press enter. Ooh, I have to go down one more. I didn't see there were 2 returns. Okay. So I'll do an O and enter there. Okay. I'm going to do the bracket percent. It is going to be based on an income. It's going to be fairly straightforward. For tax in taxes, if income is less than tax 0, I'm going to return the rate, which is tax 1. And failing that, the tax rate that's not on here is the 39.6%, so I'll return that in all other cases. Okay. Now, I'm going to press escape and write that before I do anything else because I want to have that saved. But now we're also going to go down and we're going to plot something else. And so the other thing I'm going to plot are, let's just search for plot. There we go. Okay. So I'm here in my plot line. I'm just going to, for now, delete the rest of this line and then figure out what we're going to put in here. I'm going to plot incomes versus bracket percent. Nope. I have to vectorize. Okay, so we're going to come up here. And we're going to vector bracket. We'll vector percent equals np.vectorize bracket percent. We'll call, I need to have a paren at the end of that line. We'll go to the start of this line. We'll say rates equals vector percent of incomes. Totally unremarkable. Nothing too exciting at all. And then we're going to plot the rates, and we're going to say marginal tax rate. I'm also going to update the other label. The other label looks unclear to me now, so I'm going to say actual tax rate. Maybe realized. That it's the rate. It's the percentage of your income you actually pay on taxes, right? So I'm going to go ahead and save that. I bet I'm clever enough to figure this out. Let's go ahead and run it. There you go.
Can you get this code?
Mm-hmm. This is the new thing. And what's this do? Actually, take a minute to get this working. I should pop over to the bathroom because I don't know where we're going to get the next break. You can come up here and scroll around if you want to. There's not too much code that's not on the screen. How's it going?
Yes, man.
Oh, Windows Terminal looks nice. I forgot to be able to look. It's that GPU acceleration. Wow, it's like glowy. What's working and what's not?
Okay, it's working, but I just half of my way.
Good. Very nice. Looking good. There's a distinct chance you've learned something here today, I think.
I really enjoyed this Python. When I was learning,
Yeah.
I was knocking my head on the table while I was learning, but now I kind of...
Now you like it, yeah. We're just going to do one thing. We're going to change some colors because I feel like we should. So,
You know how I learned Python?
how'd you learn Python?
I was doing a job in India.
Mm-hmm.
So my boss is actually my brother's cousin.
Oh, cool. Yeah.
So he was like older brother to me.
Mm-hmm.
So he was teaching me.
Mm-hmm.
Whenever I tried, he just gave me some problems and he told me to solve this. In the office, I used to stay like in the 10 or 11.
Yeah.
And he used to stay with me from morning 8 to like 11. And he doesn't let me go home.
Yeah, unless you
until I
like,
figure out.
yeah. See, that's how you learn. See, us poor instructors, we're required by law to let you go home, right?
Yeah. That's how you learn, you know that.
I think it's really tough, actually, and tough is like a weird way to put it. I taught a new class to the undergraduates. It's part of the crypto or the security class you'll take in the second half of the semester. It's the same material, and it's an unusually difficult class, right? And the American students, they all said they were going to drop because it was too hard, and so I said, well, here's the deal. I want people to take this class, so I'll give you all A's no matter what. And then they complained that they weren't motivated because they were getting A's no matter what, right? And I was like, I just want to lock you in the classroom and not let you leave until you know cryptography, right? But I'm not allowed to do that. So don't put on my course evals. I want you to make me show up at 8 and not leave until 11. I'm not allowed to. I would do that if I could, right? What do you think I do? I go home and already code, right? Right, like I left here tonight or last night, and basically I asked Ted at 5 because I'm worried my voice is going to give out, right? And it's like I went back to my apartment and I was learning Rust, this new programming language. Have you written any Rust at all? Have you heard of it?
I have heard it.
Yeah, it's like the new hotness. I actually didn't like it that much. I was surprised I didn't like it that much, but so spend all day learning Python, go home and nice, can learn Rust now. Yeah, get back to what I like doing. So yeah. Maybe I'll get to teach you some Rust before the end of the program. We'll see.
I'm trying to learn Flutter now.
Oh yeah, I don't know much about Flutter. Let me look that up. Flutter language.
It's more of Dart programming language.
Okay, yeah, I know Dart. That's right, Flutter apps. Yeah. For mobile?
Mobile.
Yeah. Cool.
That's.
You gonna make an app?
I made an app from Kotlin and Java.
Okay.
In Android.
You like Kotlin?
No.
Oh really? Okay, a lot of people like it. Okay.
Because I never worked that much on Kotlin, so
Yeah.
that's why. Most of the time I was working on Java and CSS, and that's Android is all about CSS and that.
They do CSS? For like GUIs or something?
It's just a front end.
Yeah. Huh. I don't know. I have done Android for years. When I did it, it was before they even had Kotlin. It was only Java. Your options were Java or Java. And I was like, great. And I was like, what do you do if they don't like Java? They're like, get a different job. I was like, okay. Yeah, the 2010s were crazy. They're like, Java's a good programming language. I was like, it is? And they're like...
No, some programmers find it very hard, you know.
Yeah, I don't know that I found it hard. I found it...
There's too much to type, and when you have to write long code, like Python, you just, if you want a for loop, just...
You write for, yeah.
That's right, for, that's it.
Yeah. I also really didn't like Eclipse. The Eclipse, yeah. I really didn't like that. Sorry. I'm back on task. Okay. The thing I changed, I changed the color here. So take a look at these lines. I'm going to highlight these lines. Remember these in your mind. Incomes, rates, label. Okay? And what I change? Incomes, rates, label, color. So you can set the color to what you want. Seems like I think these are the CSS colors or the HTML colors. I think you can put whatever in here you want. I'm going to try some different colors just while we're working on it. color equal. Can I do magenta? Can I do cyan? I don't know if this will work. Boom! Cyan and magenta. Look at them. Great looking colors. Some of the colors of all time. I bet the blue doesn't show up at all. Right? That cyan. Cyan is invisible. Boop. There it is.
I'm going to do a neon.
Yeah. No, pink's even worse. Okay, is fuchsia a color?
Letting me
Oh, is it complaining about you?
neon.
Ooh, fuchsia's not a valid color. I don't even know if I spelled it right. Oh, maybe orange is the way to go. Wonder how orange will look.
Yeah. Oh,
There it is. Orange doesn't look bad at all to me.
yeah. Pink and green.
Pink and green, good choices. Yeah, the pink didn't show up well on my screen. Yeah, it looks fine for you. Yeah, I wonder if those are Microsoft colors or something. I wonder if you can pick different types of green. So I always liked lime green. I don't know if that'll be accepted. Ooh, yeah. Reminds me of delicious
Neon.
lime. You think neon?
Did not. It gives me error for neon.
I didn't think that was an HTML color. We'll see. Yeah. Oh, you can do lime now. There you go. Got some great looking colors there. These are the citrus colors. We got lime, we got orange. I could do yellow for banana. For lemon, not for banana. Okay, there we go. Orange, glad I didn't say banana. Okay. You can put other stuff in here. I subtracted the difference. This tells you how much % you get off on your taxes. Yeah, I don't know that we care about that, but that's what we did. I'm going to show you some other chart types, and then we'll be getting to the exercise. I don't remember what the exercise is for this one. Usually I remember. I'm looking ahead. Oh, nice. We finally get to do some science. Okay. All right, so let's plot a histogram. We don't only have to do line plots. It's allowed to do other things. And so I'm just going to go back into the Python, and I'm going to make ease. I'm just going to equal this thing. I'm going to import matplotlib.pyplot as a PLT. So previously I did plt.plot ease, and I did plt.show. And that's certainly one way to do things. I'm going to do some other things now, though. So I'm going to close this, and I'm going to show that I can do plt.histogram ease. Oh, it has no. Oh, maybe it's plt.hist. I bet it's hist. There you go. And then I'm going to do plt.show. So you are not bound to only use line charts. You don't have to use scatter plots. You can also use histograms. And So here's my example of histogram. Is this working for you? Got it? Cool. We're histogrammed. And now we're just going to iterate through some other plot types. So, what do we got here? The first two means there are two elements in a single electron shell. If we had the periodic table back up, we'd say, hey, hydrogen, element 1, has 1 of 2 electrons, and helium, element 2, has 2 of 2 electrons. So how do I represent that? Well, I can say, oh, I don't have numpy. Let me import numpy real quick. Numpy is np. So the number of shells that atoms in the first row of the periodic table have is np.arrange 2. Oh, but that's 0, 1, so that's off by 1, so I just add a 1 to that, and I get the 1 and 2, right? So that's the number, and then in the next row, we go up to 8. The row after that, we go up to 8. The row after that, I think we go up to 16, 16, 32, 32, I think that's right. So I thought it would be more fun to actually do a histogram of how many electrons elements have in their outer shell, right? That's a little more interesting. So we're going to go ahead and do that. So I'm going to say that, let's make e's again, which is, I think, do I have e's? Yeah, I got e's. Okay, so for e and e's, we have, for electron in the number of electrons. This is how many we have in our outer shells. Yes, that is what I meant. Okay. Arrange. Okay. There we go. 2, 8, 8, 18, 18, 32, 32. Right? And then kind of what I need to do to get the number of electrons in general in the outer range is I'm going to create something, I'm going to call it num-e's. Num-e's is just an np.array that contains nothing, so nothing in it at all. You can take a look. And then I'm going to do my loop that I did for e in e's, and I'm going to append. Num-e's equals np.append num-e's to np dot arrange E. So this is the number in an outer shell. That is the maximum number in one given outer shell. This is all of the atoms that have that many outer shells. And we're just going to keep adding those in, and then we're going to get many num-E's, right? So this is going to be all of the counts of the outer shell electrons. So we see this would be hydrogen with 1, helium with 2, so that's off by 1. So we'll say num-E's plus equals 1. And we see hydrogen has 1, helium has 2, lithium is the third, which has 3, and so on. And this is neon. You were mentioning neon earlier. Here's the element neon. There it is. Look at it. It's a good-looking element, I think, right? And I think down here we have argon. And then down here, this is whatever element 118 is, right? And we can verify that by taking the length of num-E's. So this is the 118 elements. Does that make sense what I did there?
Yeah.
Okay. Cool. Let's go ahead and make a plot of this. Plot.hist num-E's. Okay. Plot.show. There it is. Same thing. This one's stretched out a little more. So something that was pretty interesting for me, I think, on this is there is definitely a lot of clustering at small numbers of electrons, but it levels out really quick. Like there's a lot of atoms that have 15 or more electrons, right? The Y value here is 12, right? That's a lot. So very even chart, right? So I thought that was cool. I don't worry about that stuff that much. Here's something I want to point out to you about these slides, for example. So this says we got an array, got a bar container, there's 10 artists. I'm not going to teach you what artists are. It's this internal matplotlib thing. It seems really sketchy to me, so I don't worry about it too much. When I come over here, see the exact same thing. I don't really want to see that stuff. I find it a little bit annoying. So I just throw it out using this technique. So check this out. Plot histogram. Nothing. No nonsense. All the nonsense goes away. And the histogram's still there. I can still see it just as easily. Right. So I like that a lot. So I'm just introducing that as an aside. This means ignore this. It's a social convention, but it means ignore this. You don't have to use underscore, right? You could call it saved as, and then you could look at saved as later if you wanted to, but I don't know why you'd want to do that, right? I just put it in a variable and never look at it ever again. It's great. I love throwing things out. I would throw myself out if I could. Okay, so here's the gallery. This is the histogram. I've shown you the histogram already. Here's a box plot. Let's make the box plot real quick. Plot dot, did I show this thing? Dot box plot, num-E's. Plot dot show. Oops, let's put the box plot on the same as the histogram. So we'll there we go. There's a box and whisker plot, and what's this represent? So the, I guess, median number of electrons is 11. I think this means 1/4 of atoms have 5 or fewer. I think this means 3/4 of atoms have 18 or more. The max is 32 and the minimum is 1. So this is a box plot. Have you seen box plots before?
No.
I'm not a huge fan, but they exist. And this would probably be more helpful if I plotted like metals versus non-metals or something, which I don't really have yet. Let's look at some other examples. Oh, we can do a pie chart.
Pie chart, yeah.
Yeah, we all love pie charts, right? I'm just going to do E's instead of num-E's. Okay. Yeah, look at all that nonsense that pops up. There it is. Looks great. Different systems have different colors, but I made this on the same system, right? And so I think this is per row. So this is helium and hydrogen. This is lithium through neon, sodium through argon, and then the progressively bigger rows of the table. So that's why it's increasing in size. There are many more chart types, and we are going to get into them next time. And now it is time for the exercise. And I'm going to look at what time it is. It is 3:30. I do have a hard stop at 5 today. I have to meet some people from the department. So this is a scientific computing class. I found the coolest little thing on chemistry. There's this little class called Introduction to Python for Chemistry. Now, I didn't care about the Python that much because I already knew Python, but there was some chemistry in here, and I don't know chemistry. So I got to learn cool things. And so we sort of did this already, right? But I don't know what the Arrhenius equation is, but it sure looks cool. Look how cool this looks. I think if I wrote that on a whiteboard, all of my students would think I'm smart, right? So I should learn what this is, and I should write it on the whiteboard on the first day of class and say, this is what we're learning this semester, and they'll all go, right? Like, imagine, right, if you got here at like 8 a.m. yesterday, and you came in and that thing was written on the board, right? You'd think we're really going to learn something in this class, right? So anyways, this is fun. How did I even get here? There we go. This is spelled wrong, so I'm going to fix that.
Atomic.
Yep, that should say atomic. Atmo. Yep, there it is. X-I-M. I don't know that I need to re-render for that one. I'll probably render some other time. What else am I doing? Okay, we'll run that in the background. Cool. So, there's also, this one's kind of interesting. There's a bunch of like free science textbooks around now on LibreTexts. So I've just kind of been looking at these. Stuff looks kind of interesting. I'm trying to figure out how they made these plots, because this isn't a plotting language I'm familiar with. Like, look at this thing. That was probably hard to make. My partner's a chemist and learned, I think, like Adobe Illustrator or something to make stuff. They just use graphic design software or like special effects, like for movies. They use the same stuff.
AutoCAD or something.
Yeah. But this thing I can make. I know how to make one of these. So we're gonna make one of those. Okay. So let's step through the process. Okay. The place I have too many tabs open is in my brain. It's not in my web browser. It's my brain that's getting overwhelmed here. Why do I still have the atomic orbitals open? Let's go ahead and close some of these things. That seems fine. That's the same window twice, isn't it? Okay. So, we're going to learn about electron orbitals, and also this is a good chance to show off Plotly, the much ballyhooed Plotly. I've mentioned Plotly a few times, so I'm going to show it to you. Take a look at this. This is Plotly. This looks awesome. Okay, so I can click and drag this thing. See that? And when I change it slightly past horizontal, watch, the grid is going to snap to the top and the labels are going to move. Look at that.
It's not showing me.
You don't have it?
No.
That's too bad. It's really cool. Do you have it over here? On the regular page? Like if you click home? You in Chrome?
Yes.
You want to try do you have Firefox? Try Edge or Firefox. I wonder if it's Firefox one.
Let me see on the home page.
It's matplotlib, and then click exercise. Matplotlib, exercise.
Yeah, it is showing me on this.
Okay, it has it there. I don't actually know how this works. So anyways, you can fiddle around with this. Here it is. Very cool. You can take pictures, you know. I can snap a picture. Boom. I can zoom in. I can do whatever panning is. I don't know what panning is. Oh wow, that's not what I expected. I can do orbital rotations. I guess that's what I was doing initially. I can do turntable rotations. That seems the same as orbital rotations to me, but that's okay. I can reset to default. Can I? Oh, it had to think for a while there. And then I can figure out that I should spend money on Plotly, right? So the problem is this thing has an embedded ad in it, right? But that's okay. And see, they really want me to buy Plotly AI probably. Yeah, see, it says pricing. That's no good. I'm not into that. But that's okay. So here's Plotly. Plotly is a genuinely impressive piece of work, right? And this is a model of the 3D underscore Z2 orbital, apparently. Remember how I said I want people to think I'm smart? Here's some equations. This orbital is somehow defined by the following equations. That's a constant. We know what that is. That's squaring a variable. That's raising a variable. That's cubing and then square rooting a variable. That's raising e to the power of a variable. We can do all of those things. We know how to do all of those things. Okay. What's this thing? That's a constant. This is a polynomial of two terms. We got squareds over squareds. That's a constant. Oh, so this whole thing's a constant. That's a constant. This is a constant. So we have R3D. I don't know what that is. And Y3D is E2. And I don't know what that is either. But I programmed them, and they look cool. So I also need to know what, apparently this is rho, okay? So this thing is rho. We're going to square rho. And I don't think we need to worry about z. I think we're just going to assume z is 1, okay? So 2zr, where n is the principal quantum number, which is 3. Okay, so we're gonna plug in n 3 for all of the n's. Okay. Very good. So we can plug all that in. Say we want to compare the probability distribution of 3 atomic orbitals on the same graph. The radial wave functions are for the hydrogenic, which I think that's related to hydrogen. So if we assume we're working with hydrogen, 3s, 3p, and 3d orbitals. Okay. So what are these things? Okay. So we have different r's, right? But constant. We plug in some value for r, right? I don't know what r is. We'll figure it out. And then we have e to the r. So these are all just functions of r, right? That's the only variable in here, right? Which means I could just write some function. In fact, I can here. R3s equals, nope, I'm going to do def of r. That's going to be 2 divided by 3 times np dot square root of 3. There's a variety of ways to do square root, right? I showed you this one previously, I think, right? We're going to multiply that times 1 minus 2 times r divided by 3 plus 2 divided by 27 times r squared times, I haven't shown you e yet, but the easiest way to do that is np.exp. But you can also use np.e to the negative r divided by 3. Oh, I need to return this thing. I was writing a programming language yesterday that didn't have return statements. Okay, r3's 0.5. Cool. And what is it at 0.1? Okay, it's higher at 0.1 and it's lower at 0.9, right? So I can actually plot this thing. Let's just take a lin space. We'll go from 0 to 3. What am I going to call that? Scale equals np.linspace 0, 3. Okay. And then we're going to say vals, which is going to equal r3's of scale. And then we're going to do plt.plot of scale vals. Then we're going to do plt.show. And that's some computational chemistry somehow. Seems interesting. I could do that for all 3 of these. Okay? And in fact, I did. So here's how I did them. And you'll see there's not too many stylistic differences. I used built-ins for square root and for exponentiation. All this other stuff's the same. But these are the same values. So I introduced np-exp and np square root, right? So on this slide, I couldn't fit all of the equations, right? But I showed the equivalence between R3s, right? So these values are all the same. They all line up. It's exactly the same stuff, right? And then I can plot these. Here's something that's pretty interesting. Pull this up again. Every single one of these operations is a vectorized operation. There's no if, there's no else, there's no for. So I just applied this thing directly to a lin space, and it just worked. There's no vectorizing here, right? I can, in fact, I think I can, like, say, I don't know, let's say r equals np.linspace 0, 3, okay. And I can plt.plot r, watch this. Oh, can I get it? I can do this in a single line, like so. And just put it right there. Don't even have to define a function. I do because it's easier, but I don't have to. Everything just vectorizes. The only thing I have to do is define r. Right. Super easy. Okay. That's what it looks like. You go out to 30. Here, we'll go out to 30 on this one. Where was it? Yeah, plot showing. There you go. So apparently, yeah, I got blue. Looks pretty good to me. We note this thing's a little choppy. Those things happen. Don't worry about it too much. So here we go, and I threw a legend in on this one. So this is R3S, R3P, and R3D. All right, just a little bit of computational chemistry. I added some labels. It doesn't fit on the scale. That's sad. There we go. Labeled them. I don't know what r divided by Bohr radii is. None of my business. I don't know what r is. None of my business. I literally linked you to a textbook if you care about the science of this. I just like the pretty pictures. And so, yep, I got all of this stuff to show up, and I think it's pretty cool. Yeah, maybe it's not cool. I don't know. Looks cool to me. So here's your exercise. How long is this going to take us? It is 3:45. Okay. Your task is to plot R3S, which I have provided for you, R2S, which is defined as follows, R1S on the same plot with labels, and save a .svg file. That's the exercise. Get cracking. Does that make sense? Do you know what you're doing?
R1S, R2S, and R3S on the same.
Mm-hmm.
Yeah, I can. I'll try it.
Sounds good. Mine looks like this. Is that what yours looks like? Where is it? Yeah, looks good. Well done. Did you have fun?
Yeah,
Are you a chemist now?
almost.
Too bad we have no idea what these things mean. Okay.
Yeah.
Alright, so here's my sample code if you want. I'm sure it looks the same as yours. Oh yeah, did you see this? You can put the dollar signs around them to get math font. It's not that obvious, but those S's are italicized. That's kind of cool. Alright.
What are these for? Dollar sign?
Yeah. So I think to have something up over here. Right. And I think I can say, like, what's the famous equation? E to the, oh, I don't know what pi is. Pi. E to the x, we'll say. It's not allowed. Okay. Oh, I see what I did. I just missed my close quote. Okay, yeah, right. Like, it looks like e to the x. Isn't that cool? I'm not plotting e to the x. Maybe I should have plotted e to the x. Hold on, let me plot e to the x. And p.x bar. Okay. Keyboard interrupt? Okay. I just hit something on the keyboard by accident. There it is, e to the x. Oh, that's cool, right? Yeah. So that's fun. Okay. Matplotlib. We did it. Cool. First half of pandas. And then we do the other half with SciPy tomorrow. Okay. Pandas. So you've worked with pandas before a little bit. So stop me if you get bored. Let's check stream health. Looks fine. Current bitrate is lower than recommended bitrate. Recommend use a stream bitrate of. There's almost no way I can use a stream bitrate that high. Okay. Cool. Pandas. What is pandas? Panel data. So we've looked at sort of a lot of things with NumPy, and NumPy is so fundamentally structured around the array. Pandas is really structured around panels. Panel is a lot like a two-dimensional array, but not quite. First of all, everything's labeled, which is a big deal. And second of all, not all the types have to be the same. Taxes, which we were working with, where we had integers and floats, that's more naturally panel data than it is a NumPy ND array, right? Like, it didn't really make sense to say exactly $9,275.00. That didn't make sense. The cutoff was exactly on the dollar, right? So it was a little bit strange. For my money, also there's one other thing which pandas is, which is the basis of the entire modern AI and data science boom. Many people, I think, are of the opinion that the AI boom was driven by innovations in algorithms. I don't think so. Maybe it is, right? I think a lot of these algorithms, they seem uninteresting to me. They seem fairly pedestrian. I was, while you were working on that, I was talking to one of my colleagues who's an AI researcher, and we don't understand what the fuss is about, right? But the AIs do look much better when given very, very high quality and lots of training data. And all that training data comes through pandas, right? So pandas is a big deal. It was originally built on NumPy, and so actually, I think I found this out while I was working on these slides, even though I think I knew it and hadn't internalized it. Originally, pandas was a NumPy extension, and I thought I should teach in this class. I think it's a big deal. I think it's very good for plotting. It is not a NumPy extension anymore. It is now built on, I say supercomputing technologies. It is built on Apache Software Foundation's Arrow framework, which is the cloud computing technology that's quite fast. It's probably not quite necessarily the fastest in the world, but it's really fast. So Pandas got a huge performance boost when going from 1.0 to 2.0, which it just did recently, last couple months. feel like I was using pandas in January and it was still slow, and it just became fast at some point. So that was really cool. But independent of the underlying implementation that Pandas is working on under the hood, because NumPy was a lot faster than things that came before it as well, really Pandas innovation is the idea of the data frame. Different people describe data frames different ways, and the rule of thumb is you tell people data frame is a spreadsheet, and then you don't worry about it too much. That sort of never really worked for me, because one of the things I always didn't like about spreadsheets is I thought they were hard to work with, and I don't find Pandas data frames hard to work with, right? So for me, data frame is the information that would be in a spreadsheet, but instead of having to click around and learn menus and stuff, you can just type what you want. You can directly query a Pandas data frame, for example, and that is quite different than a spreadsheet. I think there are querying engines for spreadsheets, and they're unnatural. So what are the things we can do with Pandas that are hard to do with a spreadsheet? Well, we can do automation. We can write scripts that run a large number of times. I think the closest thing to this is the Excel macro. We can do things repeatedly over and over again in loops, and we can do things consistently. If I have 1 billion Excel files, I can do the exact same thing to every single one of them in Pandas with one for loop. I don't think there's a way to do that in Excel, right? So I think Pandas is better at Excel than Excel is for the applications I'm interested in, which is using a lot of data. I learned Excel before the docx change, and I essentially never went back and relearned Excel. I learned Excel once, they changed it once, and I learned Pandas instead. I learned NumPy at the time, actually, and I have continued to use the same tools since then, right? So I have a strong distaste for spreadsheets. The thing that I kept using spreadsheets for a long time was actually all of the charts we just made. So the last thing I was using spreadsheets for was to make charts to put in papers. And now I use Matplotlib for that. And I feel quite comfortable with Matplotlib. The thing that has really made me dramatically more comfortable with Matplotlib is the idea of just like writing this script that makes a file, saves the file and looking at it, and then making small edits to the script and running the whole thing again, right? That's been very nice. I do want to sell this on being part of scientific computing. I think Pandas is the sketchiest one I included in this class. But if you look at the, I think it's like NumPy for absolute beginners. NumPy, absolute beginners. NumPy, I think, thinks of itself as being the scientific computing package, and I agree. And if you look through here, there's only two other libraries they use. They use Pandas, and they use Matplotlib. So that's why I taught NumPy, Matplotlib, and then Pandas. I did Matplotlib before Pandas because I really wanted to visualize those piecewise functions. I think if I had a different motivating example, I would have done Pandas first, because it makes a lot of sense to do Pandas than Matplotlib. But that's okay. We're going to do a bit of both, right? And we have plenty of Matplotlib left to look at. So why not Pandas? In the Python ecosystem, Pandas has recently gained a challenger. This was not anticipated, I don't think. But the Rust people wrote Polars, which is their polar data frames. They wrote a data frame language for Rust, and they ported it to Python. And I guess it's real fast, and people like it a lot, right? Pandas is showing a bit of age, right? What I expect to happen is I expect big tech to move on to Polars. For local applications, I expect big tech to stay on sort of the Arrow stuff and use Pandas to attach to it. At the really high level, talking million terabytes level, right? That stuff's all going to still be through things that look like Pandas, right? They're going to use Polars at the 1 terabyte level. And then scientific computing, I think, is going to stay on Pandas, right? Because the performance benefits from switching over to Polars are really only going to be achievable for this sort of like mid-range stuff, right? Neither Polars nor Pandas is actually running on clusters. So all the cluster stuff is still going to be running Spark, Hadoop, Hive, Pig, these sort of like big supercomputing challenges. And it doesn't really matter how we interface with them. Pandas has very good connections to Spark, which is usually how you go from small data to big data, right? So I'm letting you know, you might want to keep an eye out for Polars. If Polars does in fact take over, maybe it will, I don't know. You should immediately drop Pandas and start learning Polars as fast as you can. I did not make the decision to immediately drop Polars. pandas and start learning polars as fast as I can. I looked at polars and I said, oh, that looks fine, and then kept using pandas. Pandas pairs much better with NumPy and Matplotlib. It seems much better for science. Polars does not have a corresponding numerical computing apparatus, so I don't think you can do linear algebra in polars, which seems like a huge mistake to me. And then polars attached plotting library is Altair, which I have absolutely no interest in learning how to use, right? So the entire polars ecosystem was kind of unappealing to me. Thus far, we have only calculated and plotted data we have typed in ourselves. Yuck. I don't like typing data into a Python command prompt, right? So instead, we're going to install pandas, we're going to read in some data, and we're going to play around with that data. And we're going to do a little bit of physics and chemistry again. So here's how to install. You might already have pandas on your device.
Yes, I do.
I'm going to make sure I have pandas on my device. Oh. Cool, all good. I'm going to, I think I already have NP, right? Okay, so I'm going to import pandas as PD. There it is. And maybe it has a version. So it does, 2.1.4. Okay, very good. So I've got my NumPy, and I've got my pandas. Gotta watch the time more carefully here, because I'm going to be somewhere. Okay, 4 away. Let's take a look at, I think I had, did I have taxes in here? Nope, no problem. I am going to grab taxes. I'm going to take the whole thing. Now, this is what taxes looks like for me. This is what the data frame looks like for me. I find it a lot easier to read that data frame. I appreciate the effort the pandas people put into making these data frames actually legible. If I were to open this thing in Jupyter Notebook, it would come out styled, right? So this is just literally that exact data frame in this file. It was generated the same way. That looks really nice, and I really appreciate that, right? There's something to be said for how hard it is to tell if all of these blocks are all zeros or not. I just think that's a visually challenging prospect, right? It's too easy for one of them to be an 8. And if one of them were an 8, that'd mean I typed something in wrong, or I did a math error somewhere, but I can't tell. I can't see it, right? And the same thing is with all these zeros. There's a block of 6 zeros here, right? That's not helping anybody. All that stuff got cut out here. They only have zeros where they need it. That might just be a complaint about scientific notation, but I feel like it's not. I feel like it would have been completely reasonable to cut all of these zeros, right? That wouldn't have hurt anybody. We're going to get a file. I'm going to use some nuclear data, and we'll go through that. Oftentimes in scientific computing, someone gives you the data, right? In my research group, we generate the data with some of our students, and then we give data to some of the other students, right? So we're working with data. And I'm just going to use periodic table of the elements. In maze? In maze? That's supposed to be names. That's not even close to being names. That's in the totally wrong order. And so I'm going to grab this CSV file real quick. So how are we going to do that? Well, here, we'll open it and look at it first. This is a publicly available CSV file that is maintained by Goodman Sciences. Here is how it shows up on GitHub, which is a great place to keep your CSV files. Here is what the raw file looks like if this were only text, right? So not too much text, right? Nothing we can't manage. So we're going to go ahead and grab that file and download it. My preference with pandas is to read directly from URLs. And so I'm going to use the PD read CSV file, and I'm going to read that CSV file from a URL. Every student I've ever met always says the same thing to me. They say, hey, I tried to read the CSV file from this URL. This page is not a CSV file, right? This page is a website. It has a search bar in it. CSV files don't have search bars in them, right? If you want to look at just this file, you have to look at raw. There's no search bar on this page, right? So, how are we going to do that? Here's the URL. It ends in CSV. You don't believe me? There it is. It says right there, CSV. So that means that this is a file. What am I? Oh, I'm pressing Control and that's changing. I saw this was changing and that was stressing me out. Okay, so I'm going to copy paste this. I think I am. I think I copied that. I don't actually know copy paste on Linux. Okay, so I copied that URL, and I am going to say df equals pd.read_csv open paren quote. I'm going to drop the URL. Very good. I'm going to close the quotes and I'm going to close the parens and I'm going to press enter. And that felt like that downloaded instantly, right? That was much, much faster than creating a matplotlib plot. And I would argue this is quite a bit more data, right? When we were plotting in matplotlib, we were plotting strictly less data than this. So we can move information around quite quickly. I think of pandas as fast and matplotlib as slow. Let's take a look at df, and let's make this full screen so we can take a better look at it as well. So lots of stuff in this table. We got protons, we got neutrons, we got isotopes, we've got the number of shells. Remember we were looking at the number of shells? We've got the number of valence electrons. Oh, that's also the thing we were looking at, right? This says not a number instead of having 2 valence electrons because it's unclear if it has a full outer valence shell or an empty outer valence shell. So they don't say 2, right? But this counts up to 8, right? So 1, 1, 2, 3. We can plot all kinds of things about this straight away. Do I have PLT? Yeah, I do. So I'm going to just plt.plot the data frame number of valence. Just take a look at what this thing looks like. plt.show. There it is. Pretty interesting, right? So the valence number of valence electrons goes up quickly. Repeatedly, there's these big jumps. That's where you have the not a numbers, right, coming in. So that's pretty interesting. We can probably plot the number of valence electrons versus the atomic number. That's probably what we did already. I don't know, that's probably good enough then, actually. I don't know. This is the number of valence electrons, right? So let's go ahead and put that back. We'll open this up again. So this is how it shows up in the slides, and obviously this isn't super easy to see everything, but here we go. And you can just scroll through this. We've got fluoruvium, of course. So let's go ahead and start taking a crack at data frames. I've got to be careful about watching the time. Okay, so I've got plenty of time. What's the difference between data frames and arrays? Data frames can have more than one type, and data frames can have labels. And I didn't think that difference would matter that much, and it's a really big deal, right? The fact you can put strings in these things matters a lot. And we see it right here, right? The fact that you can have the name of an element right next to its number of electrons, there was just not a way to do that in a NumPy array. There was no way you could combine those things. So arrays don't and can't, and data frames have and can. Let's look at some subsets. I like to take a look at parts of data frames oftentimes. So we're going to take a look at, and we already looked at the number of valences, but let's take a look at another one. Let's look at the elements. There they are. We can take a look at the, is it called symbol? There you go. There's all of the symbols. Very cool. So this is just a way to poke around and look at the results of your computations, the results of your experiments, or whatever you're working with, right? You don't have to only look at one thing at a time, and this is my favorite example. We have elements and their symbols. Let's go ahead and do that. I'm going to say data frame, open bracket. Then I'm going to say a second open bracket. Why is that? I'm using a list as an index. So the data frame has an index, and I'm going to provide a list, okay? I can even say it's a list, right? I can say list equals element symbol. And then I can say df list, just like that, same thing. And I can express it all at once. Element symbol. Very cool. Right, so there's the elements and their symbols, and we'll see Many of them line up. Livermorium, named after the Livermore Labs. Moscovium, named after the researchers in Moscow. Fleruvium is named after, I don't remember a research team. Tennessine, named after Tennessee Valley nuclear program, right? So many of these later ones are named after nuclear programs. Many of the earlier ones are named after whatever they're named after. Beryllium's, of course, named after the semi-precious gemstone. Right? We can also filter things down. Something that a lot of people are interested in, especially when I talk to undergraduates and I'm trying to get them interested in sciences, they all think nuclear stuff is cool. I think it's big, it's hot, it's expensive. The cooling towers look great on t-shirts, right? I think at least Americans grew up learning that nuclear accidents create superheroes, right? So they have a strongly positive sentiment. I'm assuming nuclear energy is less popular in Japan, but they have a very strong civilian nuclear program there, right? So let's look at the transuranic elements, which are the ones used in nuclear research. So I could look at all of the elements of the data frame that have an atomic number. I have to spell it correctly. Atomic number that is greater than 92. But that doesn't give me the elements. That gives me whether something is one of the elements. So I'm going to take this thing, which is sort of just a listing, and I'm going to make it the index of my data frame. And then I'm going to see the transuranic elements. They're called transuranic elements because this is uranium, so they are past uranium. I guess the ones before that are the interuranic. I don't know. Pre. So here's the elements, and there's not too many of them. We can see all of them. Nihon, Darmstadt, Meitner. Many of these are the names of scientists that are perhaps helpful names. Mendeleev, the Russian that put together the table. Fermilabs attended my alma mater, University of Chicago. Californium. Don't know what that one's named after. That could be named after anything. I've never heard of anything like that.
California.
Never heard of it, unfortunately. In Oregon, we make fun of California a lot. It's really fun. Because the Californians, they think they have the entire West Coast to themselves, but in fact, there's about 4% of their population lives in other states, right? So we have rights too. So yeah, I've never heard of California. Berkelium could be anything. Curium, named after Madame Curie. Americium could be anything. Plutonium, of course, named after the planet.
Neptunium.
Yep, Neptunium named after the planet. Uranium named after the planet. And I don't think 90's named after a planet, right? Yeah, Protactinium. So it's just these 3 planets in a row, right? I suspect they had to come up with names very quickly when they came out of planets, and they're like, what is the thing that is the most similar to Pluto? And they put America right there. So, a very interesting idea. So, we've got some filtering here. We've got the transuranic elements. Let's get back to the actual transuranic elements. There they are, beginning at Neptunium. This is, excuse me, jeez. This is how you tell if something's bigger than 92. By the way, we should also look at what we know. Let's take a look at df dot columns. What do we actually know here? Well, we know the atomic number. We know if something's radioactive. That could be interesting. I'm going to look at radioactive. Radioactive. It's yes. Okay, so we're going to say radioactive equals yes. Promethium, element 61, is radioactive. I know that. None of my business. Right. And then many naturally occurring radioactive elements up to uranium, and then all of the transuranic elements are radioactive, right? So we can just look at all the radioactive elements. I learned something right now from pandas. I probably knew at one point in my life, but I had no idea promethium was radioactive. It's clearly named after Prometheus, who stole fire from the gods, right? And was the subject of the 2012 film Prometheus, directed by Ridley Scott, set in the alien universe. I don't know if you're a big fan of movies, but I am. I love the alien films, right? So promethium's a big element for me. There's a lot of information. Some of it we care about more than others. Are you really into boiling points at all?
Boiling points?
Boiling points. Yeah, I don't think I care about any of that information, but it's nice it's on the table, right? So if I had to figure out how to boil something now, I could look it up. If I had some hassium around and I needed to boil it off, I'd just heat that hassium up until it boils away. We should more properly look at how big the data frame is, and we're going to do that with df.shape. df.shape also works with NumPy arrays. Is taxes a NumPy array? Yeah, it is. So shape is not a new thing. That's just brought over from NumPy. But we didn't really need it in NumPy, so we didn't talk about it too much. This is a good time to do an aside. These things are called tuples. And they're basically the same thing as lists. Don't worry about them. They do not matter. Every once in a while, when we're working with a data frame, we don't want to look at it by columns, and we want to look at it by rows. For example, we might be really into table salt, and we want to learn a little bit more about sodium. So we can go ahead and do that. Perhaps I know what happened. We were at the grocery store, and we saw the low sodium soy sauce. And we're like, why would I not want sodium in my soy sauce? And then we look at it, and we find out that sodium spontaneously bursts into flames when it contacts water. And you say, I want no sodium soy sauce. And then a chemist explains to you that once it's inside salt, it's fine, and it's good for you, right? So I think that's probably what happened here. So let's look at df.iloc. That stands for integer location, right? We're going to go to the 10 indexed location, which is going to be the 11th element. Why is that? Hydrogen lives in the house on the corner, so its address is 0, but its number is 1. So that would be like, for example, I have a social security number, and I'm not going to say it while I'm streaming live on YouTube, but if you ask me nicely, I'll tell you one of the digits. And so I have a non-zero social security number even though I live on a corner, right? So that's the same thing with hydrogen. Its social security number is 1, even though it lives on the corner. Sodium lives in apartment number 10, even though its social security number is 11, right? So here's a few things about sodium. We may have other elements we have some affinity for. I believe this is argon. Nope, that was calcium. I went the wrong direction. This one's argon. Nope, that's oxygen. Finally, argon. We did it. First try. It's important to always say first try after you don't do something right on the first try. So that way people will be confused and think you did it intentionally. So some of these are solids, some of these are liquids, some of these are gases, right? Maybe like mercury is... Oh, there's technetium. Is mercury around here somewhere? Niobium, very strong. Magnets, right? So we can look up features of any of a particular element, right? We can also... I already talked about that. It can be a lot easier to look at slices. So let's look at a slice. Let's look at every 10th element. Did I do that correctly? No, I looked at the first 10 elements. Let's look at every 10th element correctly this time. So I do a step size of 10, I look at 1, 11, and so on. That seems cool enough. Maybe I actually want to start at 9, begin at element 10, and then go on. So we can take a look at all of these. And then maybe I want to look at the number of neutrons, and I find this fascinating. Neutrons, and the number of protons. So, to the best of my knowledge, the core of an atom is made up of protons and neutrons, and the rule of thumb I was taught, and I think that was because I was learning about the more common elements that are smaller, is that they happen to have about as many neutrons as protons. And that's true, but those two numbers actually get pretty different. And so that has got me thinking, maybe I should plot neutrons versus protons, and I'm going to go ahead and do that. I'm going to say, got some number of protons, and I've got some number of neutrons. Oops, it's plural. Then I can plot dot show. Good. Look at that. A little bit erratic. A little more erratic than I would have expected, right? We go all the way up to 175. I got my little overlay down here in the bottom right, so I can take a look and say, that's element number 110. It has 161 neutrons, but the next one, 112, is all the way up to 175. That's a lot of neutrons. What's this little dip right here? That's 84. No, it's 85. I don't know what 85 is, right? None of my business. And then there's other bumps here. So this thing right here is argon has an unexpectedly high number of neutrons, and then sodium has an unexpectedly low number, it looks like. So, I don't know. I don't know if that's interesting. Seems interesting enough. Perhaps it is much more interesting to plot the division versus atomic number. I have to spell number correctly. Maybe I did that right. Oh, well, would you look at that? Many of them have exactly a 1-to-1 ratio, and then they have fewer and fewer protons per neutron over time. So that can be fun. All different things to plot and show and examine and look at. You can plot the difference. I don't think I plotted the difference. Well, I could. I plotted the ratio. That's just as interesting. We can go ahead and make some plots. We just went through the PLT process. Here's a scatter plot of protons versus neutrons, which I just showed. I did a default plot, so I got a line, but we can scatter this as well. Scatter. And I think scatter is more proper, right? Ooh, that actually looks kind of cool in a scatter plot, right? Like, that looks like an equation, doesn't it? There's something going on there. That's cool. That looks like an equation, maybe, right? Some of these. But that's actually, to me, this is much more clear than seeing the line. Right, because I thought these all looked like squiggles, but in fact that's just appears to be two different series of equations, right? So that's pretty cool looking, you know, I like that quite a bit. So, we're now going to make nummies again, I think, is that right? So, much easier now. I'm going to go ahead and we went over all this, so I'm going to copy paste this in directly. Oops, got to close plot show. Oop, press X. Okay. I'm going to go ahead and copy in nummies. There's num. Oh, there's some disaster. What went wrong? Oh, I see. I have to do it piece by piece. Okay. Paste. Okay. Num is plus equal 1. Num is. There it is, as expected. I'm going to slap this onto my periodic table, right? I have some interesting insights, and I'm going to add a new column. But I'm going to do something interesting, right? The type of nummies, that's a NumPy array. But I'm going to let you in on a little secret. Each one of those rows is just a NumPy array in disguise. The real difference they have from NumPy arrays is that they have a name. All right, so let's take a look at our shape. All right, we have the shape of our data frame. That's 118. We have the shape of nummies. That's 118. And so all that's left for us is to take our 118 and put it onto the various columns, of which there are 118. And so we're just going to add it on directly. Now, if I had the wrong number, it just wouldn't work. But what we're going to do is essentially the same thing as updating list by index. But we're going to update a data frame by index. How are we going to do that? Well, I'm going to take my data frame, df. I'm going to create something, I'm going to call it outermost electrons, okay? Outermost electrons. I should note that I do not claim that the science here is being done properly. Okay? And I'm going to set that equal to the number of e's. Wow. That was easy. And now I'm going to make sure it's in there. So first of all, I'm going to check df columns. There's a new outermost electrons. That's last. Very good. I'm going to look at df integer location. So I'm going to look at a series of elements. Let's just look at step size of 20. And then we're going to look at the elements. And we're going to look at their outermost electrons. Hydrogen has 1. That sounds right. Scandium has 3. I have no idea that could be correct. Do I look like a scientist? Think carefully before you answer.
Yes, you are the scientist.
I'm a scientist. You would think if I were a scientist, I would know that promethium is radioactive, which I did not. But here we are. We shouldn't beat ourselves up about these simple matters. We can make a little scatter plot. And actually, I'm going to take a quick bathroom break. There's a series of plots you can work through quickly here, and I will go through them while you're working when I get back. How are your plots and your thoughts? Look at you hacking away at the command line. This is how you always use Python.
It's stuck. It's hanging.
Yes, it will do that a lot. There's no real graceful way to show plots. That's one of the reasons I use the save fig in the open. It's a lot more reliable. So when I encounter that problem, which I do from time to time, I'll just grab this directly. All good. plt.savefig chart.svg os.system. I write open, you write start. Start chart. Nope. I told you to write start and then I typed start. Okay. Chart.svg. And so why does this work better? Well, the operating system always can open and close programs. Python can't. Python isn't in charge of your web browser or your image viewer, right? I'm getting a different chart for some reason, but it's an entirely different problem. What am I doing wrong? Oh, well, not a huge deal. The point of the next couple slides is to give you a framework within which to understand how to visualize data in more than 2 dimensions. What worked well for me, and I don't show it here because this is quite involved, I got pretty okay at thinking about 5-dimensional data by using the X and Y coordinates in an image and then the 3 color channels. So you have red, green, and blue. And my eye could kind of differentiate them. Essentially, my eye sees 3 different colors, and then each of those 3 different colors are located in a different point in my eye. It's like, no problem, that's enough to visualize 5 dimensions, right? Once you think about 5 dimensions, is really adding the 6th dimension that much more work? I don't know, right? I'm going to show you 4 here, and that's going to be good enough. So we've got outermost electrons, which are different. They don't get to vote. They don't have a vote. Okay, I'll tell you one thing. This is my party trick. So all electrons are the same, right? How do you tell them apart? But most of the other things we count aren't exactly the same, right? So I might count cans of Coca-Cola, and they're pretty similar, but they're all slightly different, right? They might have a manufacturing defect, the color might be a little different, but all of the electrons are exactly identical. So what if there's only 1 electron? I know what you're thinking. You're thinking, don't be ridiculous. I can see more than 1 electron from where I'm sitting. But electrons are very small and very light. And the thing that causes us to be able to only go one direction through time is gravity, which holds us and forces us to go through time linearly. But gravity doesn't really work on electrons, right? Which means there's no real reason to assume that they're only moving forward through time, right? Maybe they're going in all kinds of directions. So here's a line of thinking. There's exactly 1 electron, and it's going forward and backward through time. There's some things that support this theory. For example, when an electron and a positron, which is the antiparticle of an electron, encounter each other, they both explode in a flurry of energy and cease to exist. Or is that what happens? Is actually the electron going forward in time, and then that flurry of energy is a changing direction in time, and then it's a positron. So perhaps positively charged particles and negatively charged particles are just going different directions through time. Anyways, the physicists and the chemists really hate it if you bring that up, because they don't think it's funny at all. The chemists are pretty sure that every single atom has more than 1 electron in it. And I said, no, it's all the same electron. And they're like, it's not the same electron. I was like, but it could be the same electron. And then I usually get escorted politely out of the chemistry lab. So that's why I don't know how chemistry works, because I keep asking the hard questions. Speaking of dimensions, here's our next dimension. We're plotting in X and Y, but we're also using size. To me, size was a natural thing to use for the atomic number, right? Elements with bigger atomic numbers are bigger atoms. They weigh more. So probably maybe this like really little thing over here, maybe that's hydrogen. And maybe this big old one right here, maybe that's probably some radioactive element that's artificial, right? Maybe these ones over here in the middle, maybe there's just some different metals or something, right? Let's see. This is the number of outermost electrons, so I guess this is probably denser things, right? Melting point, so we have very high melting point up here, so it's probably like tungsten or something, right? And then we have atomic number, right? So this is a way to visualize the periodic table of elements in 3 dimensions, right? And I know what you're thinking. You're thinking, Calvin, don't be ridiculous. There's no way you can fit a 4th dimension on this plot. Is that what you're thinking? Did I hear you say that? I thought I heard maybe it was someone outside. I think there was someone walking by on the street that said, "Yeah, you heard it too." Okay, yeah. I've got a plan. So I'm going to make some additional columns, and then I'm going to add them to my plot. So let's go ahead and make neutrons less protons, right? Let's just make it n plotted, right? What else are we doing? I'm gonna go ahead and paste this here. I'm gonna plt.show. What else am I doing? Oh, is it gonna work? Or am I? Oh, am I? It's a disaster. My plt.show also appears to not be working. Okay, not to worry. I have a plan. I'm gonna plot it. Then I'm gonna plot.savefig as chart.svg. Then I'm going to os.system, open, chart.svg. Oh, same chart. Okay, very good. We're winning. Okay. Would you look at that? It's 4 dimensions. See, there's the color dimension. There's the size dimension. There's the horizontal dimension, and there's the vertical dimension. I heard my haters walking around outside saying I couldn't do this, but in fact I can. plt.savefig, chart.svg, os.system, open, chart.svg, or start. Yeah, I got something goofy going on with one of my, or I wonder if my outermost electron chart is just wrong. Do you see this? It's very close, right? It's this, but it's smooshed. And so there's something in this x dimension that's wildly wrong for some reason. Yeah. So one of my x's is just absolutely enormous, and I can't figure it out. Let's see. No? Yeah, I don't know what's over there. How do I reset a plot? CLF. Okay. This will work. There it is. Okay. I had something on my plot I couldn't get rid of, so I just Googled how to get rid of it, and it went away. So, yeah, some interesting things here, right? These appear to be related elements. These appear to be related elements. These appear to be related elements. But, without the benefit of color, I think even with just size, I wouldn't have noticed that these two things that are layered right on top of each other are not the same. But that does suspect, these are probably in a similar place in the periodic table. So, what was color? Color was neutrons less protons, right? So very odd. These things are probably in different rows of the periodic table. So they have the same number of outermost electrons, but they have roughly the same boiling point and roughly the same number of neutrons less electrons. Does that maybe mean that the difference between the numbers of protons and neutrons is related to the boiling point? I don't know. So I'm guessing a chemist would actually be able to do something with this graph, or at least say, Calvin, that's random noise. You're plotting nothing. And I would say, but if I were plotting nothing, why does it look so good, right? And if you make this really small, then the colors get bigger. Oh, look at that, right? I'm gonna. It looks like art, right? You could hang that on your wall, right? That's cool looking. So there's a lot of good times that can be had with the combination of science and matplotlib. So we've got that. We'll proceed. we've got to look out for keyword arguments. These are keyword arguments. They are different than the other arguments to the function in the following way, and let's take a look at an example. I'm going to make something called triple. No, I'm not. I'm going to make something called quadruple, because I already made triple on the slides. You've already seen that. So I'm going to make quad x. Quad is, of course, my order at a coffee shop. Get a quad espresso. We're going to return 4 times x. If you want to be really pedantic, you can just add x to itself 4 times. Everyone hates that. No one likes it when you do that. So I do that to annoy people, which is really fun. That's one of my more endearing traits. I can look up what quad of 4 is, and I can look at what quad of x equals 4 is. So you can always specify these things. Maybe we want to make another example. Maybe we want to make, what else do we want to do? myexp. There's an exponentiation in Python already, but we're going to raise something to a certain value, and we're going to call that m for the mantissa, and then by default we're going to have some power, which we're going to set to be equal to 2, okay? And then we're going to return 2 to the m, right? So myexp of 100, of 10, that's going to be about 1,000, right? But I may also want to raise 10 to the power of 2. How do I do that? Oh, I got to redefine this. myexp of 10. We also may want to raise 10 to the power 2. Well, we can't do that this way, but we can do it by saying myexp of 2 to the 10, right? But that might feel kind of backwards to us, so maybe we want to say my exponentiation, I want the power to be 10, and I want the mantissa to be 2. So we can change the order of our arguments by specifying their names. And so that's kind of one of the niceties of how to work with Python and keyword arguments. I, generally speaking, do not like this. Just to editorialize, it feels really underdocumented and weird. I think you should just keep adding things in order. But with these big complex APIs deciding how to make plots, there's maybe just no graceful way to do it, right? So they say X, Y, S, C. X values, Y values, size values, color values. And those are the only 4. I'm not allowed to go past 4 in matplotlib. If I have to plot things in 3 different color spaces, I have to write my own custom code for it. And I have done that, and it looks awful, but it is good for understanding. So, sometimes mathematicians use it, things like that. Okay. Probably last-ish thing to cover today, and I think we were supposed to get about halfway through this, so we are exactly on schedule. We went the same speed today as yesterday, so good job. Sometimes you want to drop things. When you want to drop things, maybe you added something to your data frame by accident, right? Maybe there's 4 heliums in here by mistake. That'd be a little cooked, right? We don't really want 4 heliums. And sometimes you have extra stuff that you don't need. And here's my favorite example. The atomic number, the number of protons, and the number of electrons are always all the same value. And that's 3 of my 28 columns. Very close to 10% of my data is redundant. So I'm going to get rid of these things. Let me demonstrate this real quick. So we'll look at df atomic number. One thing I don't like about pandas, and this is why pandas is never going to win me over, I hate typing column names. You see why? Just look at this. I did my absolute best. I corrected a typo, and I was still wrong because I just forgot it didn't have a space in it. Number of protons. These things are kind of all looking the same to me. Really?
R is missing.
R is missing? Wow, yeah. Thank you. I would have been here for minutes. I never in my life would have guessed there was an R in electron, even though I say it out loud. My good friend Electronald McDonald is how I remember there's an R. Okay, So those numbers are all the same, so let's get rid of them. We're going to get rid of them using a keyword argument, columns. Let's take a look at df shape. It's up to 30 now because we added outermost electrons. I'm going to tape my data frame. I'm going to set it equal to a new data frame. That new data frame is the old data frame with the following change. I drop something. What do I drop? I drop a number of columns. Which columns? I'm going to drop a list of columns. That columns includes number of protons and number, nope, it's in parens. Nope, it's in quotes. Quotes and parens are entirely different things. Number of electrons. Close quote, close bracket, close paren, press enter. Didn't work. It's because it's plural. There we go. Took out the trash. And the trash is protons and electrons, right? See, it's odd to list the number of electrons in an atom because all atoms contain at most exactly one electron because there's only one electron in the universe. So that's why I removed that. I was worried the science was incorrect. Summaries. There's okay, we're going to get smaller for this again. A lot of ways to look at data. Shape is one obvious way. We can look at describe. What's describe do? This provides a series of summary statistics, right? So there are 118 atomic numbers and masses, so there's 118 of everything. The mean of atomic numbers, that's not surprising, that's half. Atomic mass, much higher, right? Number of outermost electrons peaks at 12.5, and neutrons less protons. We have around 26. That seems pretty high to me. Standard deviation, so pretty high variance here. The minimum is -1, so there's some element that has more protons than neutrons. It's hydrogen. That's the only one. In general, you have to have at least one outermost electron, but that's because I defined it that way, right? You could equivalently argue that those things, when we have 2, 8, 18, 18, or 32, maybe those have 0 outermost electrons, right? We've got the quartiles, right? Each quarter. So here's the medians. Always fun to look at the difference between the medians and the mean. For some values, it's the same. 142 is very close to 45. 11 is very close to 12. 24 is very close to 26, but they're not exactly the same, right? And then we have the maximums, right? Our maximum atomic mass is very high, right? 295. So there has to be an enormous number of neutrons in there, right? So that's all fun. Info is also helpful. Let's take a look at info. Mostly this tells us types. This stuff's pretty interesting to me. These ones that are objects, I suspect that means they're strings, right? So I suspect phase is solid, liquid, or gas, and I think it's written that way. I probably wouldn't have done that. I would have done 0, 1, or 2 and written a note somewhere that which ones represent which. A bunch of these things are floats. Discover is once again string. So most of these are numerical values, right? I do want to reiterate. If you look at this thing here, that could be a NumPy array, but of all things, this can't, because it has integers and floats in it. And there is absolutely no way group should be a float, right? Because there's a discrete fixed number of groups. Let's look at it. All those things end in 0, right? So that's just weird, right? We can look at the columns. We've seen columns previously. Something I want to point out, info had parens at the end. Info is a function. Let's see. What am I doing? Shape is not a function, right? Columns is not a function. So some of these have the parentheses at the end and some of them don't. The way I figure that out, I just try both and see which one doesn't give me an error.
It's the best way to do.
It's called science. Yeah, we're conducting experiments on pandas, right? Actually, do not say in public, I'm conducting experiments on pandas. Do not say that. That'll get you beat up by a zookeeper, right? Shape. And then we can also do a bunch of things column-wise. So I can say, oops, df dot melting point. Melting point's a great example. What's the max? Wow, I did not think it was going to be 4,000 degrees. And I think those are the big Celsius degrees, too.
Is it Celsius?
I think those are Celsius degrees.
Wow.
What's something that we know of that's liquid at room temperature? We need mercury. I don't know what mercury is. Symbol. We tried. Look at all those errors. Oh, wait, maybe it's... I have no idea how to find out which one mercury is. What else is liquid at room temperature? I mean, there's not a lot of elements we Oh, we can do iron. I also don't know the number of iron. Let's look at like the middle 20 and see if there's anything we recognize.
Mercury, right?
Yeah, did you find mercury? There. Oh, it's 80. Okay.
80, yeah.
Okay. So this is going to be liquid at room temperature. Oh, I got thallium by accident. Yep. Okay. This one is liquid at room temperature. Melting point 23. It's Kelvin. Those are degrees Kelvin from absolute zero. I think. What's iron? Did I catch iron? Yeah, I don't know.
26.
26?
Yeah.
Oh, God. The off by ones are getting me. Okay, so here's iron. Yeah, I thought iron's boiling point was around 3,000. So I think this is off by a little bit. So it's indexing from 0. All right, and we will begin with using loc tomorrow. We're at 49 of 102, so that's as close to the middle as we can get. So, all right, good work today. Did you learn anything?
Yeah.
Cool. And definitely say yes even if you didn't. So that's the trick. Okay. All right. Good seeing you. I'll see you back here tomorrow at 9. I will give you a ride to the airport. We'll leave around noon. Maybe we'll try and find an Indian restaurant on the way to the airport. If you find one, I'll stop, basically.
Yeah.
Yeah. Thank you so much. Hope you had a good day.
Thank you. Oh. It's giving me warning for severe thunderstorm.
Oh. Yikes.
About at 9 p.m.
Oh, okay. That's not for a while. We'll be fine. Oh, in here or in Florida?
It's here.